It's a pleasure to have all of you here today for this webinar that is done by 3 Prima projects. The idea arises from these 3 projects to put together these 3 projects that were funded within the Prima Foundation, within the first Prima call in the section 1 on water management, in particular on water management and reuse. So this first call the project started in 2019. So all the projects are close to the end with like 6 months postponement due to COVID. So all the project will end this year, by the end of this year. So we decided to go together for some activities to exploit, to share, and to improve the benefits of these 3 projects and to make the public aware about these relevant activities. So I would like to thank in this introduction a lot to some person. First of all, Marco Orlando. So all the Prima Foundation was close to us. Marco and Sara, of course, in this organization, they fully approved and supported our idea to have this joint event. And also I would like to thank Viola, Stevo, and all the colleagues from the other project. I'm the coordinator of the FIT4REUSE project, but we did this work together with the coordinators and the partners of the other 2 projects, WATERMED and DSWAP. So welcome again. I'm so sorry because I'm at home with COVID, so I'm not in a good shape today, but I asked Marco to help me in this for this webinar. I will try to be with you as much as I can. So thanks again. I leave the floor for the introduction to Marco Orlando. Thank you very much.
Thank you, Attilio. Thank you very much for opening this meeting, and I can only join you and thank not only you, and I'm really sorry to hear that you have COVID. So, thanks twice for your commitment to being in this webinar. I mean, it's very nice to see that now these projects are getting to an end, but you are ready to share some results with the scientific communities and well, the Mediterranean communities in general, to speak about some results, to share knowledge, and so on. I really want to congratulate all the projects because I think they are successful, but I mean, of course, it will be even more interesting once the projects are officially closed to further disseminate their results. Today we have a first occasion to do it. I want to acknowledge really the commitment and the effort of the coordinating teams of the project, and also the project teams. Everyone really helped with the organization of this webinar. Of course, the 3 coordinators, the University of Murcia, the University of Bologna, and the Volcani Center from the Agricultural Research Organization. But again, all the partners have contributed to the preparation of the meeting and will contribute with their presentation today. As you know, most of you know me already. My name is Marco Orlando, and I'm the project officer responsible for the water management thematic area at the Prima Secretariat. I guess that most of you know Prima already. It's the Partnership for Research and Innovation in the Mediterranean area. It's the most ambitious research and innovation joint program funding, let's say, research in water management and agriculture sectors that has been ever launched in the Mediterranean area. It's a partnership between the European Union and 19 participating states from Europe, North Africa, and the Middle East. And of course, the main aim of the program is to use research and innovation, and of course, the projects that you are implementing as a tool to better address the common challenges that the Mediterranean is facing, like water scarcity, the impact of climate change, the food insecurity, and the unsustainability of the agricultural sector, agricultural practices. So again, back in 2018, we launched this call for proposals that was very competitive, and it was a tough decision, but I guess we selected really the 3 best projects: FIT4REUSE, WATERMED 4.0, and DSWAP. And that call, the main aim was to finance projects that would have a good impact in the region through the valorization of non-conventional waters and by trying to achieve better water use efficiency through a better management of the water cycle in agriculture. So very, very relevant topic that today we will explore a bit with you. Of course, topics that are considered very important in the Mediterranean, where water is greatly misused, where water bodies are shrinking, where they are getting more polluted, and of course, where water scarcity is further exacerbated by climate change. So, of course, this webinar today will offer some food for thought. We know that we have to rethink the way we use water and also the way we reuse water. We have to develop solutions which have less of an environmental impact. We have to look closely at the interlinkages between water, but also ecosystems and energy and food. We have to provide end users and decision makers with the necessary evidence, support, decision support tools to better manage water, better allocate water in contexts which are increasingly characterized by competing water demands. And of course, the big challenge remains that with a growing population, we have to try and produce food with less water. And in this context, again, if we have a better ways to manage water use and water allocation, and if we better valorize non-conventional water resources, this can be very helpful. So, especially for non-conventional water resources, the discussion is very interesting because we have to look not only at technology, but at policy options and at regulations, governance issues. And of course, we have to address some concerns that the society, industry, regulators may have. So today, it's a great occasion for me and for everyone who is following this webinar to learn about the projects, the work that you carried out during these challenging times, because of course you faced the pandemic shortly after the beginning of the projects. We will have several sessions. The first two about the project support to policymaking and water planning, as well as their contribution to sustainable water management in agriculture. Then we will have a roundtable discussion addressing the barriers to sustainable water management in agriculture with prominent panelists from different international organizations. So I look forward to listening to the presentations. It's almost 9:10, so I would like to close this brief introductory speech, and thank you very much again, all the people who contributed to the organization of this webinar, and thanks again to all the projects team. And I will stop here and give the floor to the coordinators for the first session. Thanks everyone for the attention.
Thanks, Marco. Good morning, everyone. My name is Miguel Angel Zamora, researcher at the University of Murcia, partner of WATERMED project. And I will be the moderator of the first session dedicated to project support to policymaking and water planning. In this session, we have 3 presentations, one of each PRIMA project. I would like to remind the audience that the session will be concluded by 5 minutes of question and answer, and that the chat has to be used to pose questions, including also the speaker to which the question is addressed. After this explanation, I give the floor to Célia Manaia for the first presentation. She comes from the Catholic University of Portugal, which is partner of the DSWAP project. Célia, you have 15 minutes when you want.
Good morning for the introduction. I will be speaking about the project DSWAP. Let me start the DSWAP, which stands for Decision Support-Based Approach for Sustainable Water Reuse Application in Agricultural Production. This project is in place, represented by 10, is a consortium of 10 partners from Israel, who are the coordinators, here represented by Edith Citrin. And we have also Germany, Cyprus, Spain, France, Italy, Portugal, and 3 companies. Among these 10 partners, 3 are companies from Spain, Cyprus, and Israel. We have a budget of around 2 million euro. And the big goal of this project is to develop decision support tools and also technology for the quality of water, to produce water with quality adequate for water reuse and with minimal impacts in soil. So this is our goal. We are organized in 3 technical and experimental work packages. One that is dedicated to the development of module treatment, so the processes of wastewater treatment. The 3rd work package is dedicated to the design of support tools, and work package 2 is like a bridge between both, that aims at developing and establishing diagnostic tools, and also support the project in the assessment of the quality of the treatment. These are the integrated objectives. So the diagnosis, the optimization, development, and integration of the different processes. My brief presentation today will be about monitoring systems to support policy making and the water management planning. I will focus on antibiotic resistance, and I will do this in 2 different aspects, because antibiotic resistance is an important contaminant that occurs in soil, but also because antibiotic resistance can be regarded as a sentinel, as an indicator of contamination in soils due to wastewater reuse. What do we want to evaluate in this kind of monitoring? The efficiency of the treatment processes, assess the impact in the receiving environment, and also, whenever possible, to meet policy recommendations. We have nowadays 3 major methods to monitor antibiotic resistance, or microbiological indicators in the environment. One is based on culture-based methods, is probably the most traditionally used, and the one that is used, for instance, for the determination of E. coli that is present in most of the legislation. We have quantitative PCR, which is really a targeted method and quantitative method, and we have metagenomics, which is really powerful to give us an overview of the whole microbial community that we have in a given environment. When we have any of these methods, and this is true for all of them, we have some challenges that regard the high limits of quantification that we have in microbiology in general. When we compare with chemistry, microbiology have high limits of quantification. And sometimes, because the receiving environment have a very important, a very rich microbiota, sometimes it is very difficult to assess the footprint, the impact that we would like to assess. Regarding culture-dependent methods, they are normally based on the monitoring of Escherichia coli. Some subpopulations of antibiotic-resistant Escherichia coli can be used, and it is possible, and we can see here a decrease from the inflow and outflow. This study was made before with wastewater treatment plants around the world, and we realized that indeed it can be a powerful method, but we were afraid that in this case would not be the best approach, since we are dealing with the waters already with a high degree of decontamination. Are waters that in principle have very low loads of Escherichia coli. This is the kind of results that we obtain with quantitative PCR. So we have a quantitative indication of the abundance of different genes and different microbial groups, if that is the aim. And we can see quantitatively a decrease across a treatment process is what we have here. So we have an indication of the decrease, for instance, after secondary treatment and not that much on tertiary treatment, but it is possible to make this kind of quantification. And this is the kind of data that we obtain with metagenomics, which is indeed a very, very broad overview of the microbial community. It is adequate and it can provide very important patterning of antibiotic resistance, in this case, of different environments, although to assess impacts may have limited capacity. In this project, in work package 2, we focused in 2 case studies of soils irrigated with treated wastewater. One that was being implemented in Israel in our real fields that are used for some years. And in Cyprus, we had lysimeters, which were finished here. Thank you very much for your attention.
Started to work on the beneficiaries and on the stakeholders, adopting a quintuple helix approach. So looking at the different typology of stakeholders, including education, so both looking at public research and other type of research and training centers, economic actors, so private farmers, media, environmental related stakeholders, so for instance related to the water market and the political system, so water policy makers. So looking at the different interests that the stakeholders and the researchers in particular find in let's say policies related to wastewaters. So and we did apply this quintuple helix approach, looking at stakeholders in the countries that are engaged in FIT4REUSE. So Spain, France, Italy, Tunisia, Greece, Turkey, and Israel. And how we did work, let's say starting from this, from taking this quintuple helix approach, we carried out a literature review, so looking at secondary data analysis from both from academic and literature in order to combine let's say the material, the articles, the scientific work that is carried out within the research environment, integrating it with all the reports, the policy pieces, policy brief, strategies that are developed at the national level and European level by policy offices, policymakers, and so on. We carried out a legal review, so a textual analysis of the EU and national legislations and regulations based on previous studies. And we carried out also a sentiment analysis in order to look at the perceptions of the different stakeholders. In order to take advantage of the knowledge of the project, we also carried out interviews with the key stakeholder in the sector, including, let's say, starting from FIT4REUSE project partners and building, let's say, together with the partners in order to engage institutions and other, let's say, leading actors in the field. And we did realize a number of feedback sessions, carrying out focus group during water reuse days. That has been one of the features of the project. So let's say within this method, we developed an inventory on the current legislative and policy frameworks, which is, I would say, a live inventory. Since we are continuing to work on it and continuing to develop it, and on the right side of the slide of the screen, you can see some of the material that have been collected and integrated in this inventory. So the inventory was also the base, as I was anticipating, of the sentiment analysis, so of the understanding of the perceptions that the different stakeholders have about the current legislative and policy frameworks. So we try to understand the hindrance factors for water reuse that are ranging from stricter limits at the national level compared to the EU standards, cumbersome water governance, lack of financial incentives, high reuse cost, lack of agreements, unclear paperwork, lack of trust of farmers, but also on the consumer side, lobbying against water reuse. So we try to identify all the factors that might create constraints in the development of an effective framework for water reuse. We identified what can be defined as neutral aspects for water reuse. In this case, we included the legislation divergency between regional, local, and national level, or between national level in neighboring countries, and also circularity, both a trigger for some consumers to opt for a more sustainability integrated product, but also a source of scare for others. And also triggering factors for water reuse are important. And triggering factors are including the perception of water scarcity, and as an urgent issue, the EU single benchmark to harmonize the standards adopted at the EU level, the EU legislation that removes bottleneck due to different standards, or that streamline the water reuse processes. Obviously, a strong triggering factor is the political will, the lobbying in favor of water reuse, the incentives in water tariffs, and the innovative legal framework. And so what we try to do, looking at both the factors that are somehow representing constraints for the development of a water reuse framework, those that are neutral and those that and those that are potentially positive factors. We created, let's say, we developed an overview that is going to be, let's say, important to look at the future. So to understand what are the drivers that represent, let's say, important hotspots or important turning points that could be played, changed, or revised in order to improve the legislative and policy framework in the future. So the new regulation will lead to a wave of adaptations in both member states and non-EU countries. And what research should try to understand within the different factors that we have identified and shared together, should look at gathering systemic empirical insights into the effects of the EU regulation, should investigating the influence of public engagement, which is very important, should engage citizens in understanding research on water quality and reuse, but also in producing research on water quality and reuse in terms of, let's say, the adoption of citizen science approaches, and should use citizen-operated water monitoring technologies based on sensors combined with advanced data analysis techniques and maps. So we created a background through this inventory to understand the current policy framework, to understand the current drivers, we had an understanding together with the stakeholders about what the research should do in the future. And what we are doing now, at the moment, we are working on developing a policy for a site in order to identify the major drivers of change that are expected to facilitate or hamper the diffusion of non-conventional water resources. So again, we are working with the stakeholders in order to streamline and identify among the drivers that we have already included in the framework that we shared before. We want to identify those that are more important in the different contexts. So taking also into consideration the differences at the national level. Once we have identified the major drivers of change that are, let's say, potentially contributing to step up and improve the water reuse policy and legislative framework, we want to analyze the implication of the different drivers. And looking at the drivers, analyzing their implications, we want to identify potential policy interventions that could target the selected drivers. So what are the policy options or the policy measures that could either minimize those drivers that have a negative effect or maximize the benefits of the drivers that are leading a change, so bringing a positive policy change and a positive change in the system. So so this is where
time is up.
Yeah, so this is where we are now, and this is the type of work that we will carry out in the incoming weeks and months before the end of the project. Thank you very much for your time and for the attention.
Thank you, Matteo. Okay, and the last presentation is, I give the floor myself. It's about the WATERMED project. Do you see my screen?
Yes.
Okay. Sorry. Okay. The last of the three Prima project is WATERMED 4.0. The complete name of the project is the efficient use and management of conventional and not conventional water resources through smart technology applied to improve the quality and safety of Mediterranean agriculture in semi-arid areas. We have three key points in this project. One is the application in agriculture. The second is the water management, and the third one is the governance, the water governance. Related to the overview of the project, the main aim of WATERMED project is to develop and apply a DSS based on IoT, of Internet of Things, to manage the whole water cycle in agriculture, mainly by monitoring water resources, water demand. That include economic, energy, social, and governance factor that can influence in water use efficient in the Mediterranean agriculture. Here you have the different partners of the project. University of Murcia, that we are the coordinator of the project, and also in Spain we have two public institutions, the Central Board User of Vinalopó BASIN and the Spanish National Research Agency. One private partner in Morocco, two universities in Algeria, the Turkish Water Institute in Turkey, and finally the Fraunhofer Institute of Solar Energy System. The main objectives of the project we can summarize in 5 points. First of all, adapt and implement technology for reclaimed water and reuse. Using technology that we have, adapt technology that we use in past project. Concretely, we have 2 projects, the Eurostar project, and the second is the drain use water treatment from the Life Drain Use project. Some of the partner of this project was partner in these 2 past projects. The second objective is the study. Is to study, adapt, and implement new sensor, new communication protocol for monitoring and control of water distribution system using the last technologies, Internet of Things, services, service technologies, etc. The third one is more related to agricultural productivity in the Mediterranean areas. My mission the use of water and fertilizer by optimizing the management of fertilization. Sorry. We use new technology based on real-time in situ using different sensors that we will see now. Another important objective is the use of agrophotovoltaic application. In this case, we have 2 important aspects. For one hand, to use this technology to reduce the irrigation needs through the shadowing. And the second important thing is, for example, in isolated rural areas, when you don't have electricity, you are, in this case, you are able to produce self-consumption electricity through the solar panels. And finally, the last objective is related to the development of socio-economic studies to improve the governance, the water governance in the Mediterranean countries. One of the key points of this project is the engagement with this different user and stakeholder that we through different studies. And part of this is we had to do different training and education activities that we will see later. Okay, summarizing an easy view of the WATERMED platform. You can see here on the left, you have the inputs, the data acquisition of the different sensor, the classical sensors were what we call remote sensor, that, for example, satellite images, and agronomic data, etc. And on the right, you can see the different services or different advices that you can get from the platform, from the user interface, alert, warnings, different evaluation, and fertigation plans. Here you have a more detailed view of the platform. So in this case, you can see that this is a modular layer design, range from sensor development to intelligent data processing and using machine learning and other tools. One important point here is that each of these layers is based on open and standard initiatives. For example, such as one provided by the FIT4REUSE European Community. And this is an important point to join different technology for other control system, legacy control system that you have in the different infrastructures. Again, you have a simplified view with inputs. In the platform, you have with different modules, different calculations, and finally you have the outputs that you need for optimization of in agriculture, policy management, water management, etc. One interesting things related to the architecture of this software platform is the data integration of a very different source of data. And this is one of the main problems to be solved is the integration of the different technology elements, SCADAs, his drawing software, different independent sensors, third-party services, etc., etc. You can see, of course, using standard and open protocols, IoT protocols, firewall protocol, etc. And we can see the software platform as a hub of services. Here you have a view of the main is a snapshot of the front end of the platform, and you can see that it's a set of different services that you can use depending on your depending of the stakeholder, the end user, etc. Here you have you can see you are able to have a different analytical process based on big data frameworks, if interoperability aspect with external services like his, different end user interfaces to provide relevant analytic dashboard, etc. Related to the agronomic services, in the platform, you have you have to take into account the different aspect related to crops, crop type, coefficient, plot information, plant type, plant analysis, etc. The same with the soil, and finally, all related to the irrigation aspect. And with all this information, you are able to have the this has been developed in this in the different pilots of this project. You have the different irrigation scheduling, fertilizing, and smart forecast irrigation or smart irrigation forecast. Related to the first of the services, you have a lot of options related to the define, modify irrigation problems, use the advanced mode to specify a lot of parameters, previews and different with different access to the timeline of irrigation program, etc. Related to fertilizing, we are able to specify different fertilizers, provide recommendations, calculate fertilizing quantity depending of the season, depending on the crop, etc., etc. So really the platform is a base of acknowledgement related to this. And finally, the same with forecasting of irrigation using different methods. Here you have one of them related to the estimation of evapotranspiration with the, in this case, with the different inputs that you need for this methodology. And using again the standard interface for connect the different modules of the platform. The first key point of the different the first key point of the of the project is the governance and all related to this. So related to the governance, we make different actions. One of the most interesting action is the integration of a network of bathymetric sensor, more than 1,000 sensor in the in this case in the Vinalopó basin, that allows to see the evolution of the groundwater water bodies in the basin of this river. The second action, important action in this project is the different index mapping that we did in this case in the area of one big area of Argelia with index of vulnerability, risk, hazards, and all of them integrated in the same platform thanks to open layer technology, of course. Here you have a snapshot of the software related to the Vinalopó basin. And here you can see that it's available the last values of all these sensors, historical graph, comparison of series, interoperation with standard program, etc. So this software with this software is able to see the evolution of the groundwater we can see easily the evolution of the groundwater in this basin. Here you have the second experiment in this case in an area in Argelia with using different methodologies. We are able to to graph vulnerability index, hazard index, and also risk index mapping. So finalizing with the related to the governance. So you can see in all the three pilot that I will show you now. We make a socioeconomic analysis and an evaluation of the agricultural production in all of the three cases. So related to the three pilots, in the case of one of them it was in Spain. It's in Júcar Vinalopó basin. In this case, the challenge was the overexploitation of aquifer in this basin. We study the water efficient in irrigation, optimization of fertilizer, using the platform services for integral management for water resources in this case, and the socio-economic indicator and water offer governance aspect, as I say. The second pilot is in Argelia in the region of Chelif Plain. In this case, the main challenge was the groundwater salinity and water scarcity, the soil degradation and pollution of the groundwater. In this case, this pilot was the test of the agro-photovoltaic technology. Again, we use the WATERMED platform for irrigation and optimization of fertilizer, but also for the demonstration for the results in agrivoltaic system and hydroponic installation that we did in this area. And finally, again, the socio-economic indicator and water governance aspect. And finally, the pilot studies, the Konya Basin in Turkey. In this case, the focus was in the intensive use of water for agriculture with scarce water resources. In this case, we did the irrigation and fertilizing scheduling again, and also the suitability and feasibility of using reclaimed water in irrigation.
Miguel, time is running out. Sorry.
Yeah, I am finishing. Summarizing the developments and extension, evapotranspiration, anomaly detection, soil moisture estimation, machine learning, using of machine learning and estimation of images, indexes using the satellite images from Sentinel constellation. And finally, the last of the objective was the engagement with the stakeholder. And related to this, we had different webinars with the different stakeholders and workshops. And that's all. Thank you very much to everyone. So it's time for question and answer.
Hello, Miguel. We have some questions I see in the chat.
Yeah.
So maybe Matteo could try to answer a little bit. We are a little bit late, so very quick answer, Matteo here, and then we will complete the answer into the chat directly.
Okay, some of them, thank you, Attilio. So some of them have been already addressed in the chat. So I will start from the last one that was not addressed from Hassan. The question is regarding the legislative framework at national level and standards for using treated water in agriculture. What sense make having different standards when the EU market is open? Well, two elements here. First of all, there is a new regulation that has been published at the European level. So that is, let's say, solving out or sorting out the differences that we had at the European level. So that was a major effort towards the harmonization of the legislative framework. But at the same time, FIT4REUSE is not looking only at the EU level. We are looking at the Mediterranean level, so engaging also non-European countries. And that is why there was a need for looking at what are the practices and the legislative and regulatory measures in the different countries. So, but your, let's say, your observation is absolutely right. And then I tried to answer about, let's say, on the first question on the on providing an example about the sensors. It could be sensors that might be connected to a web app to measure water quality. And then there was a third question on if there is any material available from NORA. And I already posted in the chat a link to the deliverable that is already published. And plus, at the moment, we are working on a scientific article, but you are very welcome to come back to us for any further information or curiosity or need in case you have them. And I think, Attilio, these are all the questions that we have got on our
Thank you,
slide.
Matteo. Thank you, Matteo. Maybe, Miguel, there are some questions for you.
Yeah, I can see one question for me, and I think that we have time. So the question is how the IoT tool was designed. Do you involve the stakeholder through multi-actor approaches to identify their needs and requirements? Yes, of course. In all the process. I think that's very important. And for example, one of the partners of the project, the private company in Morocco, another companies that is not directly in the project, but they advise us about how to design the different tools. On the other hand, other stakeholders like agriculture, big agriculture, a big company of agriculture has been involved in this process. So the answer is, of course, yes, it's necessary, it's mandatory. So the last question, 1 minute for the last question, that is for me too. We install measures temperature, humidity. I don't remember now. So we did that combination of sensor from the soil and from the satellite images. So this the result of the different advices that we provide in the platform is a mix between the classical soil sensor that is usually used by the technological companies in agriculture, but also that is new. They using the drone images and mainly satellite images and analysis of these images and about with the different indexes that you are available in this with these satellites. Okay, thank you very much to everyone. I think time is up in related to the first session. So I give the floor to the second moderator. In this case is Célia. When you please, Célia, when you want.
Thank you. Good morning again. I'm Célia Manaia, and I will be moderating this session, which deals with the project's contribution to sustainable water management in agriculture. This module will be comprised of three major, it will have 9 speakers that are associated with different topics. Technological solutions, which will be the first, water sustainability, assessment of impact and benefits of the innovative systems and the technologies, and the last one, sustainable water management decision support tools. So we will start with the technological solutions, and our first speaker is Luigi Rizzo from Salerno University. I would like to recall everyone that we wait for your questions and comments in the QA section, and this will be discussed at the end in the last 5 minutes of this session, which will be at 11:30, just before a brief break. So Luigi, please.
Thank you, Célia. Can you see my presentation?
Yes, we can.
Okay. So good morning, everyone. So as Célia introduced, my talk will be on wastewater treatment and our work in the DSWAP project. So as you can see, the title of my presentation is Tertiary Treatment of Urban Wastewater by Solar Photo-Fenton. So a feasible solution for small wastewater treatment plants. So this is the framework of my presentation. I will introduce briefly the main challenges in tertiary treatment of urban wastewater, the European wastewater reuse regulation, and the state of art in the tertiary treatment of urban wastewater. And then I will talk about our results, some of our results about the application of solar Photo-Fenton to tertiary treatment of urban wastewater. So here you can see a list of the main challenges in tertiary treatment of urban wastewater. For example, one is the disinfection and disinfection byproducts. You know that disinfection process result in formation of toxic byproducts. For example, in Italy, the Italian regulation for wastewater reuse regulates trihalometanes, which are the main chlorination byproducts. And in Italy, we have a limit of 30 microgram per liter. And disinfection byproducts are also included are taken into account the EU regulation on wastewater reuse, in particular with regard, as we will see, to the risk management plan. Other important challenges in urban wastewater are contaminants, the so-called contaminants of emerging concern, which include different contaminants typically occurring at really low concentration in wastewater, from nanogram per liter to a few microgram per liters. These include pharmaceutical, pesticides, personal care products, and so on. And even in this case, European Union is taking care about through the watch list on these contaminants, and recently with the EU regulation on wastewater reuse, where they are recalled into an annex, as we will see. And in particular, in Europe, we have the case of Switzerland that actually has a regulation to upgrade urban wastewater treatment plants to remove contaminants of emerging concern. Also, Germany is moving in such direction by upgrading wastewater treatment plants. Other challenges in tertiary treatment of urban wastewater include antibiotic resistance, as Célia explained us in her previous presentation, and microplastics. So just a few information about European regulation on wastewater reuse. Here you can see the table with the reclaimed water quality requirements for agricultural irrigation. And you can see that according to the reclaimed water quality class, the European legislators set a different limit for E. coli, BOD5, total suspended solids, and turbidity, with the E. coli a really stringent limit for class A class water. And what is really interesting in the European regulation for wastewater reuse is Article 5, where the wastewater treatment plant managers are requested to finalize and implement a risk management plan. In this risk management plan, the wastewater treatment plant managers are also requested to evaluate the possible risk related to contaminants of emerging concern, microplastic and antibiotic resistance, as you can see in this summary of the Annex 2 of the regulation. So in this slide, you can see a flow chart of a typical wastewater treatment plant. And in particular, the scope of our work in the DSWAP project was tertiary treatment by solar Photo-Fenton, as I explained before. So the tertiary treatment of urban wastewater, typically you can see the main processes and technologies applied for tertiary treatment. In particular, ozonation and activated carbon adsorption are among the best available technology to remove contaminants of emerging concern. As I explained before, for example, Switzerland and Germany have upgraded some wastewater treatment plants to remove contaminants of emerging concern, either by ozonation or activated carbon adsorption, in some cases also combining both processes. Advanced oxidation processes are among the most interesting emerging processes and technology for tertiary treatment of urban wastewater. These processes rely on the capacity of producing radical species, among which the main one are hydroxyl radicals, that can effectively remove contaminants of emerging concern and even inactivate effectively microorganisms. Among these processes, one of the most investigated as a tertiary treatment of urban wastewater is solar photophantom. Solar photophantom actually is effective at acidic pH. So when this could be a problem in urban wastewater treatment plants, because as you know, the pH of wastewater is neutral. So in this condition, in order to avoid acidification and subsequent neutralization, chelating agents can be used to form complexes with the iron species and avoid iron precipitation at a neutral pH. So in the scope of our work package in the DSWAP project was to develop solar photophantom process for small wastewater treatment plants. And we compared a new chelating agent, briefly named IDS, with a consolidated EDDS chelating agent. And here you can see the experimental setup that we've performed experiment in the so-called raised weight pond reactors under natural solar light. And we investigated different conditions by comparing IDS chelating agent with EDDS. We also coupled the solar hydrogen peroxide process with solar photophantom because solar hydrogen peroxide was found to be more effective in the inactivation of bacteria compared to the solar photophantom. And so we also tried this combination. Here you can see some results of our work. For solar photophantom with IDS, you can see that the removal of contaminants of emerging concern, we investigated a mixture of 3 contaminants of emerging concern spiked at 200 microgram per liter initial concentration. And so you can see that solar photophantom EDDS here was more effective than in the removal of these pollutants compared to IDS. We also compared the processes coupling the solar photophantom system with a pre-treatment with sunlight hydrogen peroxide. In this case, you can see that we observed an opposite effect. In this case, solar photophantom with IDS was found to be, in terms of inactivation of E. coli, was found to be more effective than solar photophantom with the EDDS process. In particular, we did not observe so significant difference between solar photophantom with IDS and solar photophantom with IDS coupled to solar hydrogen peroxide. So these results are really interesting, and right now we are ongoing the investigation of these processes on antibiotic resistance. So in conclusion, contaminants of emerging concern, pathogens, and antibiotic resistance determinants are challenging pollutants for tertiary treatment in urban wastewater. And the compliance with the European regulation for wastewater reuse can be another task for wastewater treatment plant managers. In particular, if when implementing the risk management plant, the wastewater treatment plant manager may be asked to also make the effluent in compliance with the removal of contaminants of emerging concern. In particular, consolidated methods for tertiary treatment of urban wastewater have some drawbacks, as for example, ozonation result in the formation of toxic disinfection by products. And for example, in Germany and in Switzerland, typically they use a post-treatment with filtration or adsorption. So these consolidated methods may be not effective in addressing some emerging challenges. And so in this case, alternative solutions such as solar photofenton can be an effective solution, in particular for small wastewater treatment plants. This is some colleagues that collaborate in this work in the DSWAP project. And this is all from my side, and thank you for your attention.
Thank you, Luigi, for being on time and for the interesting presentation. We move now to the second speaker, Francesco Fattoni, Marche Polytechnic University, and is member of the FIT4REUSE consortium. Francisco, please.
Célia, and good morning, everybody. I'm going to share the screen. Just a second. You should see my screen now, right? In full mode.
Yes.
Perfect. Okay. Thanks a lot again. I'm one of the partners of the FIT4REUSE project that is coordinated by University of Bologna and Attilio Toscano. And I'm going to talk about the compact and intensive solutions that we have validated within the FIT4REUSE project. In particular, I will start from a comparison between the conventional and innovative solutions that we have tested. And then I will go quickly through the 3 pilots that we have validated in long term in Italy, in Tunisia, and in Greece. And finally, I will also introduce our work for developing and adapting the water uses management guidelines in order to have also a look at the Mediterranean basin. So as to go to conclusions. So as also Luigi mentioned before me, actually the new regulation is probably facilitating the wider application of water use. Here in Italy, we have one of the most well-known examples, for example, in Milano, of treatment plants that were achieving the water quality for use by conventional treatment that is active sludge plus tertiary filtration, in this case is sand filtration and disinfection. That can be UV, can be parasitic disinfection. So this conventional treatment train is actually quite consolidated in large treatment plants. So our aim was to think about decentralized systems, more rural areas, but anyway, more compact solutions. So we have tried a combination of intensive and nature-based solutions that will be the topic of our next speeches, so as to find a fit-for-use combination for the Mediterranean framework. So what we have developed, well, we have focused on different operation units, and here in Italy, we have developed a combination of a compact solid liquid separation that can separate a cellulosic sludge that can also be used to produce biogas or also to be fermented to produce compost. And after that, we have an anaerobic membrane reactor that is a combination of USB plus submerged membranes. Then we have UV that can be eventually combined also with advanced oxidation, but this was not the case in our specific investigation. And molecular imprinted polymers, that was our most innovative experiment to address the targeted removal of contaminants of emerging concern as a tertiary treatment or quaternary treatment, but also in combination with biological treatment. Well, this train is more complex than conventional train and can allow also the fertigation system reaching the class A water quality according to the last regulation of water use. Well, so results were of the combination of the operation units were very positive. What about the molecular imprinted polymers? Well, we found that these solutions, these nano solutions, in combination with biological treatment, were not effective, even because in these small and decentralized systems, we have a granular system and deflocculation. So when you have a floccular sludge, these are not able to remove contaminant of emerging concern, and our target was diclofenac as representative compound, but as tertiary treatment, we have good results that can increase the removal of emerging contaminants, in particular pharmaceutical. But in combination with that, we were also addressing the potential of nutrient recovery. Why? In this treatment train, the possible added value can be the fertigation. If fertigation is not possible, and this is the case of sensitive areas or nitrate vulnerable areas, for example, we can combine the anaerobic system with a solution to recover nutrients. This was developed by the University of Bologna. And in particular, in this ion exchange, we have developed a solution that can recover both nitrogen and phosphorus. And here you can see how the system was set up, how this was validated. Even models were finally validated. So we have all the design data to scale up the system. And you can see the curves of adsorption and desorption together with the operating capacity that are needed to finally design the system. I would say that for phosphorus, results are quite promising, and we have to bear in mind that phosphorus is a critical raw material. So for phosphorus recovery in tertiary systems, this can be a quite promising solution. But we were addressing intensive solutions also without membrane systems. Why? Because membrane are very energy intensive. So we were trying to combine directly an aerobic system and nature-based solution. And this was the case of the Tunisian pilot plant that was developed and validated in Tunisia. In such a case, we were able to find the best either retention time. Our aim initially was to go very low in terms of retention time to have a very compact system. But as you can see, when we go lower than 24 hours, when we go to 6 hours, the volatile fatty acid to alkalinity ratio exceeds 0.4. This means that the anaerobic process is a bit unstable. But for higher retention time, we have a relevant removal and conversion to biogas of the organic substance. So even in this case, compact solution with a retention time that will depend on the type of organic substance that we have in the effluent. Finally, in Greece, we were developing several solutions, both nature-based and compact. As for the compact solution, the nano-zerovalent ion was tested for long term for the removal of both contaminated emerging concerns and heavy metals. And the results were pretty positive because, as you can see here, the removal of contaminated emerging concerns ranged from 70 to more than 95%. And also the removal of targeted heavy metals were very relevant. So even in this case, as a treatment after the secondary treatment, after the biological treatment, this combination can allow improvement of removal of these contaminants when this is needed according to the water use risk management plan. Why? Because when contaminant of emerging concerns are targeted, we have to think about a fit-for-site approach. So in such a scenario, we were analyzing the current regulation and we were validating this regulation for conventional advanced solution. And we were analyzing the adaptability of this regulation to the Mediterranean basin. In addition, last August, we had also the publication of the guidance to support the application of this regulation. That is a very practical support. So we were evaluating how this can be then extended to the Mediterranean basin, because this, of course, is a European regulation. So what about these guidelines? Well, we were analyzing the systems and we were analyzing the data categories and the different NDUs that we can have for the high quality treated water. And of course, the bottleneck is the quantity of data that is necessary to use this water. So with this in mind, we are considering the data and the site and the sites of the plant to understand the frequency of monitoring that is needed to deliver safe water use with minimal risk. So here you can see an example how we were combining the multi-barrier approach that is necessary for minimizing the risk with our fit-for-use compact solution. And thanks to this combination, as you can see here in the bottom of this slide, the combination of compact and nature-based solution can reach the EU target and can reach also the minimization of the risk. Further to this, and this is the final slide, we were including in the methodology both the quantitative microbial risk assessment and quantitative chemical risk assessment. And even in this case, our work was to find the minimum number of data that you need to deliver this risk assessment, because of course, taking into account rural areas and decentralized solution, we consider that we cannot have a huge amount of data as it is the case in centralized solutions. So as a conclusion, well, of course, we observed that already conventional plants that are applying tertiary treatments such as sand filtration and UV, for example, are already achieving even Class A water quality standard. But when we think about the compact solution and energy efficient solution, that was our point, the water energy nexus. In terms of energy efficiency, we were trying to combine the anaerobic system with nutrient recovery or reuse or fertigation in order to have the different possible scenarios. Well, we demonstrated how a suitable combination can reach not only high water quality, but also the realization of multi-barrier approach by a proper combination. And we were also addressing the removal of conventional and non-conventional contaminants. And well, as for molecular imprinting polymers, these are effective as tertiary treatment, but not in combination with the biological treatment, while neonazovalent iron are quite promising, again, as tertiary quaternary treatment for emerging contaminants and for heavy metals. Thanks a lot for your attention.
Thank you, Francisco. It is now time to move to the next theme. What the sustainability assessment of impacts and benefits of the innovative systems and technologies. And the first speaker will be Hedi Citrin from the Agricultural Research Organization in Israel, and is a member of the DSWAP consortium. Hedi and all the other speakers, I would ask you to be on time because we are slightly delayed already. Thank you.
Sorry, can you see my screen? Perfect. Okay, so thank you, Célia, and I thank the organizers. And I'm going to be talking about one of the modules. Célia gave a general introduction to the DSWAP project at the beginning, and we have several modules. You heard about the advanced oxidation process-based module that Luigi presented. I'll be talking about effluent storage reservoirs, and I won't go into too many details. Of course, we know that when we talk about wastewater reuse, and specifically wastewater reuse for agriculture, we have criteria that need to be met. As we can see here, these are Israeli standards. And the reservoir, we're specifically focusing on fecal coliforms or E. coli. And as you can see here, of course, national, international regulations all have criteria that are either based on fecal coliform or E. coli maximum levels. But as was mentioned, it's very, very possible, maybe probable that in the future, criteria on both national and international levels are going to also require evaluation of antibiotic resistance indicators, whether it be quantification of specific antibiotic resistant bacteria, or as Célia introduced, the use of molecular techniques to quantify specific antibiotic resistance genes. Now, in Israel and in other parts of the world, reservoirs, and you can see one example from southern Israel here, are often used for both storage of effluents that are used for irrigation, so more as a logistic solution, but also as a post-treatment stage where water quality is actually improved in these reservoirs, and they can be chlorinated. And of course, this improves the quality, the microbial quality of the water prior to irrigation. And indeed, in preliminary analyses, we looked at the inflow, secondary effluent, tertiary effluent, and the reservoir using both culture-based and culture-independent analyses. So what's interesting is if we look, for example, at the 16S ribosomal RNA gene, which is an indicator for total bacterial abundance, we see that there's a drop by about 2 orders of magnitude between the secondary effluent and the tertiary effluent. But there's actually no difference in the total amount of bacteria, maybe even a slight increase between the tertiary effluent and the reservoir, indicating that we have pretty much the same number of bacteria. But if we look at the drop in E. coli and fecal coliforms, and specifically cephalotaxime-resistant fecal coliforms, we see a reduction in the number of fecal indicators and in the antibiotic resistance indicators, such as these antibiotic resistance genes that were analyzed. You can see there's a reduction between secondary and tertiary, but also a strong drop between tertiary and the reservoir. And this brought us to conclude, this isn't only our conclusion, that environmental ecosystems can be very, very good mitigators of bacterial fecal contamination and antibiotic resistant gene contamination. And within the framework of DSWAP, work package 1C was to try to develop these eco-stabilization reservoirs to further reduce pathogen and antibiotic resistant gene levels by understanding the abiotic and biotic factors that influence them. In other words, if we can better understand how these ecosystems work, we can perhaps improve them and therefore improve, of course, the water quality that's being used for irrigation. So the general framework of the project was to do this by first starting with microcosms, going to larger mesocosms, and then going to a large-scale system on the Israeli beta site. In practice, what we decided to do is, since we already had a beta site from the beginning, and one of the modules that's being analyzed in the project is this membrane aerated bioreactor from a partner company called Fluence in Israel. The nice thing about this pilot site is that we were able to build this 4,500 liter reservoir, which constantly received the effluent, so secondary effluent from the MABR reactor. And so we decided, instead of going from microcosm, mesocosm to the beta site, to start directly with the beta site and see if we indeed see the phenomenon that we previously saw with the large scale reservoirs. And indeed, when we did analyses, first, if we look at the chemical parameters, of course, here we're seeing in blue effluents from, so raw sewage. So this is basically primary effluent. The red is secondary effluent, and the green is effluent from the reservoir. So we can see that most of the reduction of organic carbon occurs in the MABR, in the secondary treatment module, as well as reduction of total nitrogen. Interestingly, with pH, we see a very, very large variation of pH in the reservoir, along with total oxygen, and this is apparently due to photosynthetic activity that we see in the reservoir. When we looked at removal of both total E. coli and cephalotaxime-resistant E. coli, we can see that there's a significant removal of 1 to 1.5 log units between the sewage and the MABR, but a similar reduction between the MABR and the reservoir. And when we look, I won't go into all the details, at a wide suite of both mobile genetic element and antibiotic resistant gene indicators. And this analysis was done in Célia's lab at the Catholic University of Portugal and in the lab of Professor Christophe Merlin at the University of Lorraine. We see that there's a reduction again, of 1 to 1.5 log units of most of these parameters between the raw sewage and the MABR and the MAB on the reservoir. But what's interesting is that when we normalize this to the total amount of bacteria, we see that the normalized reduction is much, much stronger in the reservoir than it is in the MABR. And to conclude, we can say that the MABR in the reservoir removed most of the sewage-derived organic carbon and nitrogen, and simultaneously E. coli and antibiotic resistance genes and mobile genetic elements, which dropped by about 1.5 and 1 log units respectively. But, and this is very, very important, the reservoir, the relative abundance normalized to the 16S gene was much, much higher. And this suggests a shift in the microbial community composition. And I didn't have time to show this, but we did analyses both in Célia's lab and at the University of Dresden of both bacterial community and eukaryote community composition. And what we see is that in the reservoir, there's a significant shift in microbial community composition. And this indicates that what's really reducing these levels is the change in community and the resilience of the local ecosystem versus in the secondary treatment stage where we're removing sludge. So that's basically the conclusion, is that the removal of antibiotic resistance genes and bacteria in the MABR is mostly a consequence of biomass removal. So in the secondary treatment, we're removing biomass, and that's the primary trigger of improvement of microbial water quality. Whereas in the reservoir, the mitigation is more strongly linked to natural attenuation associated with the development of native microbiomes. And these prevent the establishment of wastewater-derived communities and associated antibiotic resistance genes. And to just jump to what's being done right now, now we're basically trying to zoom in and identify factors that can improve the water quality. And we're looking at two things. Based on some mesocosm analysis that we did, we found that when there's a sediment in the reservoir and we're using TUF, this is volcanic-based rocks, we found that there's an increase in the removal of fecal indicators. Another thing we're very, very interested in doing is, of course, covering the reservoirs. A big factor contributing to water loss is, of course, evaporation. And by covering, we can, of course, reduce evaporation and reduce algal blooms, which we get. But we're not sure if this is going to have the same effect on the ecosystem. And therefore, right now, we're testing both the impact of sediment and the impact of open versus covered reservoirs on the water quality. And with that, I thank everybody. And of course, we have questions at the end of the session.
Thank you, Hedy. It's now time to move to the next speaker. In the meanwhile, please load your questions in the chat, in the QA area. There are some questions for both for Francisco and for Luigi, so you are welcome to maintain this dialogue in the QA section as well. Okay, now it's time to move to the next speaker, Remy de Klerk from Ecofile, and is a member of the FIT4REUSE project. So Remy, please.
Okay, hello, good morning, everybody. Can you see my screen? It's good?
Yes.
Okay. Okay, you see the right one, the full screen one. Okay. So good morning, everybody. I'm Remy de Klerk from Ecofile, based in France, working in FIT4REUSE. And I will talk about the experimentations on the field on water reuse in agriculture that we have carried out in FIT4REUSE. And some of the results, I could unfortunately not present all of them, but I will focus on some of the results we got on our pilot sites. In FIT4REUSE, the main objectives of the irrigation test experimentations we have carried out on pilot sites are to identify adapted and sustainable practices for water use in agriculture. They are tailored to be very to answer to very operational questions from farmers. In France, Ecophilae, we are a consultancy company. We got many feedbacks coming from farmers, and we try to build those tests in those 3 sites to answer very specific questions still raising in France, in Italy, and even in Tunisia about water reuse in agriculture. So we got 3 pilot sites in FIT4REUSE, one in Tunis run by ISBAT, another one in Cesena with some experimentations in Bologna run by Unibo, and another one in Montpellier. What we decided is to build a common framework protocol, a common protocol framework for all those 3 sites to be able to carry out cross comparisons between the 3 sites on some experimentations. And we decided to define the experimentations that were not exactly the same in all the 3 pilot sites into 5 categories. Related to 5 major impacts of irrigation with reclaimed water. The first one is about irrigation drippers clogging. I will go on with it later. The second one about sanitary hazards related to pathogens and micropollutants, especially with a strong focus on micropollutants in France. And the one about salinity and sodicity hazards related to salinity of water, reclaimed water, and the impact on soil and crops. And the one about fertilizers properties and economies, but of course, depending on the reclamation technologies that are used before. And some very related to the presentation of Mr. Citrin before about water quality in storage systems. What is the trend, the evolutions of pathogens under different conditions? Unfortunately, I didn't detail all the results of this impact. I could not talk about everything, but that would have been very interesting comparing to the first presentations. But we made comparison between open and closed storage and comparing the impacts of E. coli evolutions between open and closed storage, of course, according to depths, according to circulations of water into the and flow into the storage systems. And some of the conclusions could be quite interesting to be compared with the one in Israel before. But we also could see that in some conditions we got some drop of Escherichia coli, and of course also on some other pathogens that are the one followed in the EU regulations, in the European regulations for water reuse. But we could talk about that later. And then I would like just to highlight you, so here you can have a look to the different pilots. So in Tunisia, that was focusing on tests on pots. In France, we got a pilot sites with lysimetry cases, open fields, and different types of storage, closed and open, as you can see. And in Cesena, they carried out also tests on lysimetry cases under different conditions and for different crops like tomatoes and peach trees. So as I said before, we defined a common framework. So it was not to be very exhaustive, but at least we got some parameters for each of the impacts that were monitored in all the sites, so to enable cross comparisons between the sites. So if I just take, for example, for the one for salinity hazards, all of us, we have been following conductivity and TDS, and of course in soils, the compositions of exchangeable cations, cationic compositions, and yield, of course, in crops behind. So now just a focus on some of the results, the main results about drippers clogging. So those are the results for France. So when we try to follow the impacts on drippers clogging, so we use lengths of 100 meters of different lines of drippers, and we were following clogging, and the indicator to follow clogging was the loss of flow that we could see and measure at the last dripper. And we tested for that several modalities for treatment. The one was punctual flushing, another one was punctual treatment with chlorinations and nitric acid. Another one was we continue treatment with chlorine acid and acid nitric. And if we compare just the first result we had, of course, after 250 hours of irrigation, we could, of course, and that was our control experimentation, we could see the depletions in flow of 50% in using reclaimed water without treatment, not without treatment, without treatment to avoid clogging compared to conventional water. And then if we compare the results we got with flushing and punctual chlorinations and acid nitric, we got a decrease of flow loss of 20 to 40% compared to the reclaimed water without any modalities. But the best results we got was with continued chlorination and acid nitric, which enabled to decrease flow loss by 60 to 80%. Of course, for that, we need to compare that to the cost. So we made a balance in terms of cost. What are the costs for treatment for those modalities? And behind, what are the benefits in terms of renewal of drippers for farmers? And our conclusions were that the cost and the balance is quite similar for punctual chlorinations and with continued chlorination and acid nitric. And for all of them, this enable economy or almost by 50% compared by reclaimed water without specific modalities of treatment to avoid clogging. Then to continue with the main, some of the results we got, considering micropollutants, we carried out tests. Those are the results in France as well. And we monitored some specific components for micropollutants at different points of the chains, at different measure points of the chain between the raw wastewater to the output of a reed bed filter, and then after reclamations technologies being here aerated with bed filter plus electro-oxidations. And of course, we carried out the same test in crops, here in tomatoes and in soils. And we could see that we didn't find, we could not find, of course, no, that was not, of course, but fortunately, any component into the crops by themselves, into tomatoes, and of course also, fortunately, of course, into soils as well. What is interesting there, it's the results first, but of course also the method that we used, because here the main difficulties was to target specific micropollutants, and specifically for a small wastewater treatment plant. Because in water reuse, when you want to target micropollutants, it's maybe, let's say, even to carry out analysis in huge wastewater treatment plant, because you know that there will be micropollutants. But when you're dealing with small wastewater treatment plant, it's very dependent on the people, on the local people, what they use and the time, and there is no mix and no average possibilities. So we had a huge work in advance to screen a lot of micropollutants in the raw wastewater, to be sure at what time in the hour we will have the most chance to identify with the lab characteristic that we have, to identify some micropollutants and to target the one that will be the most probable to go through the whole water reclamation chains to end up into tomatoes and to soil. So let's say that this protocol was tailored for small wastewater treatment plants and how to monitor and how to find to be sure to target specific micropollutants there. Another test that we carried out, this is a cross comparison between Italy and France results. We compared the results that we have for in terms of fertilizers savings. So the result that we have that for peach tree and for salad, this the use of reclaimed water using, of course, different types of water reclamation solutions, unable to save around 35% of the nitrogen, around 10% of phosphorus, and depending on the crop's requirement for potassium, it could go to 100% to less than 10%. And for tomatoes, we also got different results. mainly considering that we didn't have the same wastewater, reclaimed water quality that was used on the crops. So it was not very feasible to carry out a cross comparisons between the two sites.
Remy,
yes.
Sorry, you need to resume your presentation.
I need to what? Sorry.
To conclude.
Oh, okay, and I'm finished. And I mean, there is so much more to do to talk about those results, and I will be available to talk about them later if needed.
Thank you very much, Remy. Very interesting presentation indeed. Please discuss this on the QA area, and also we hopefully will have some time to discuss some of these results. So the next presentation will be by Burcu Yazidi from Turkish Water Institute, and is member of the WaterMed 4.0 project. Please, Burcu.
Good morning to all. Thank you, Célia. I think now you are able to see my screen. Okay. This is Burcu Yazidi from Turkish Water Institute. We are one of the partners of the WaterMed project, and within the scope of this project, we are conducting a case study, which is on water use in agriculture irrigation. So we have chosen this topic as our main focus in Konya Closed Basin because water reuse is still not widely applied in Turkey, and also Konya Closed Basin is one of the hotspots in terms of intense agricultural activities. Agriculture areas cover nearly 60% of the basin, and that said, the basin has a semi-arid climate with very scarce surface water resources. Therefore, most of the water demand is met from groundwater resources, and apart from that, the crop pattern consists mostly of water-thirsty crops. So at the moment, agriculture uses up to 94% of the total water available within the basin, and currently water potential of the basin cannot meet the water demand, which is expected to grow in the future. So currently we are facing groundwater depletion of over 30 meters in the area, which has also led to formation of sinkholes throughout the basin. So that's why the purpose of our study was firstly to investigate suitability and feasibility of using reclaimed water for irrigation, agriculture irrigation purposes. And apart from that, as part of the WaterMed project, we are focusing on optimizing water use efficiency in agriculture by developing irrigation plans through the WaterMed platform. And also we are integrating, as mentioned by Miguel in the beginning, social, economic, and governance factors as well. So taking a look at our demo site, we have divided our demo site into two sections where one half is irrigated with reclaimed water and the other half with groundwater for control purposes. And for our test crops, we have chosen sugar beet and corn, as these are the most widely grown crops in the area and also among the most water-thirsty ones. And treated wastewater is supplied to the demo site from Konya wastewater treatment plant, which provides advanced biological treatment with disinfection units, so microbiological activity is not expected. And also we have deployed meteorological stations and soil sensors in order to come up with irrigation plans for the platform. So of course, throughout the irrigation periods, we have conducted water quality analysis for reclaimed water in order to see if it's fit for use in irrigation. And in Turkey, this is regulated by the communique on the technical procedures for wastewater treatment plants. And there are three quality classes depicted by this communique, which are based on the parameters of electroconductivity, TDS, SAR, sodium chloride, and boron. So our reclaimed water was fit for use for irrigation purposes. And of course, we have conducted soil quality analysis and plant quality analysis as well. But for the last year, in the first term, we did not observe any significant effects on the soil or plants. But our studies are still ongoing for this year, and we'll see if anything changes. So coming to our product yields, before I go into the details, I should mention that for the first year, we have let the farmer do his irrigation practices as is. This is because we wanted to compare the practices in the ground with the amount proposed by the platform. So for corn, in the first year, we have observed a 7% increase in corn yields with reclaimed water. And on the contrary, we have observed a 9% decrease in sugar beet yields with reclaimed water. And this decrease in sugar beet yields could be attributed to the presence of excess nitrogen within reclaimed water. And if we take a look at the irrigation that is applied in practice by the farmer with the amount proposed by the platform, you can see that for corn, the amount proposed by the platform was 16% higher than the amount applied in practice. Whereas for sugar beet, the amount applied in practice by the farmer was 20% higher than the amount proposed by the WATERMED platform. So this also indicates that the decrease in sugar beet yield could be a combination of both excess irrigation and excess of nitrogen presence in the reclaimed water. So apart from this field study, we have also conducted a survey with farmers and authorities in the basin in order to understand their perceptions with regards to using reclaimed water in agricultural irrigation. So of course, one of the first things we asked them was if they would prefer or recommend using reclaimed water for irrigation, and 92% agreed on using this alternative water source. And the second question we asked them was if which types of fruits or vegetables they would grow with reclaimed water, and 91% said that they will irrigate plants that are not in direct contact with reclaimed water, which is followed by fruit tree irrigation and plants growing in direct contact with reclaimed water. When we asked them about their hesitations on reclaimed water use, 55% of them indicated that they would avoid reclaimed water irrigation because of the contamination and the health risks it may impose. And 57% of them stated that they would avoid consuming vegetables and fruits irrigated with reclaimed water, again, due to health risks it may contain. And that said, 89% of the respondents stated that if they get regular updates on reclaimed water quality analysis, this would alleviate their hesitations. So we also inquired them about the effectiveness of administrative capacity with regards to sufficiency of legislative framework on reclaimed water use, confidence in authorities, and also efficiency of institutional coordination and cooperation. And as you can see from the graph, all of these items need certain improvements in order to enhance the uptake of reuse applications in agriculture irrigation. And last but not least, we asked the participants of the survey how much they are willing to pay for reclaimed water if it's going to be used in irrigation. And 90% stated that they would prefer to use it if necessary incentives are provided. 79% said that they would use it if it's cheaper than current water tariffs, and 67% said they will still use it if it's the same price as the current water tariff. So to conclude our first term results for the reclaimed water use, we did not observe any adverse impacts on soil and plant quality. Actually, reclaimed water has even a tendency to increase crop yields, but of course, here we should take into consideration each crop's fertilization requirements. And reclaimed water also provides the benefit of reducing fertilizer needs of farmers. But of course, as in the previous presentations mentioned by our colleagues, it's important to study the impact of other pollutants as well. And that said, the Turkish legislative framework needs certain updates, and the terms in it must be more clear for the users. But farmers are willing to use reclaimed water. But again, to elevate the hesitations, transparency and participatory approach is essential. And also authorities, of course, highlight the need to carry out more studies on this issue in terms of finding fit-for-use solutions for economic and technical feasibility, and also to alleviate health impacts. Thank you very much.
Thank you.
I'm from the Fraunhofer Institute for Solar Energy Systems, ESA, and part of the WaterMed project, where I'll be presenting on the assessment of applying hydroponics and agrivoltaic systems to water-scarce areas. So thank you to Miguel for introducing the WaterMed project. So I will save a bit of time and jump directly to the location we were working in, which was the Shelif Plain in Algeria, where we installed the agrivoltaic system and the hydroponics. I was mainly responsible for the agrivoltaics. Our partners, University of Meyssonnier, were more specialized in the hydroponics, but I'm presenting on their behalf as well. In this pilot, we had some specific objectives, which were, and also to mention that actually, before I get into the objectives also relate to some farmer sites, which were off campus from the university site. But I'll only be going over the installation, which is at the university campus. But overall, the pilot objectives were to set up a system for monitoring of low quality water uses, so high salinity groundwaters, and the application of modern irrigation practices to save water and nutrients. To increase crop productivity, control quantity and nutrients and fertilizers, and to improve the soil quality and environmental effects of a more efficient water management in agriculture, including treated wastewater. And lastly, to analyze the potential of agrivoltaic applications. That's in relation to the provision of electricity from off-grid systems and the shading effect of the agrivoltaic systems and the impact they have on crops. So the region where we have the small demo sites installed face some common challenges. The Shelif Basin is known for its fertile land and high agricultural production. However, groundwater supply is still the primary water resource for irrigation, which means that water scarcity, groundwater and soil salinity are major constraints in actually increasing agricultural activity in the region. That being said, farmers are often using low quality water, which could have a negative soil and crop performance impact. For the specific site where we installed the agrivoltaic system and the greenhouse which houses the hydroponic system, the University of Meyssonnier, it was located here just close to the university lecture halls at an area of 2.5 hectares. And yeah, this is where it was equipped with the installation, which you can see from a Google aerial map here, and is very small, the greenhouse, which you'll see later. So for the agrivoltaic system, going directly into that and the overview of the system, it was installed at over an area of 600 square meters, and just south of that is a reference field of equal size, so unshaded, uncovered by PV modules, and just north of the system was the greenhouse installed. The system is designed to provide 45% shading. So we know from previous experience here in Germany that some systems up to 30% shading show favorable results for crop yield, so improving crop yield and protecting crops. And we estimated a 45% shading. There's no perfect shading rate. There's a lot of science behind the crops that could possibly benefit from this kind of shading. We went with an estimation. The planned orientation was this east-west system. So the modules facing east-west, the system running north-south at an azimuth of 90 plus 90. It was eventually installed at 72 degrees which is fine because it still results in homogeneous distribution of light. What you'll see that's interesting is that the PV modules were oriented in a V shape for rainwater harvesting collection, which is not the only way to harvest rainwater, but as you can see by the impacts and benefits, which I'll go over later, we wanted to investigate the design of this orientation. And lastly, the fields, both the agrivoltaic and the reference field, were irrigated by a drip irrigation system. And like I mentioned, the objectives were to study the impact of shading on the crops and the soils, the energy yield of the specific orientation and V-shaped design, and the rainwater harvesting potential of that design. With that, we had some expected benefits and impacts from previous research, which we've seen over time here in Germany and France, Italy, Asia, and North America, that the shading provided by the PV modules is expected to alter the microclimate below the PV module. So that's the soil microclimate, soil moisture, soil temperature, and that would hopefully result in improved growing conditions for the crops. So better crop growth rate, quality, and yield. That's through reduced evapotranspiration from the shading, and which ultimately results in reduced water irrigation needs. Also with that, physical protection of the crops and soils, investigating the rainwater as a non-conventional water source, and finally the energy use, especially in the agricultural value chain. Just a brief overview of the results. We did notice it's only from a very short period and 2 harvest cycles, so not conclusive. But what has been shown so far is that there is a marginal amount of moisture retention at different layers, so 20 centimeters, and overall compared from the agrivoltaic system compared to the reference field. However, at 40 centimeters, we see that the reference field actually has a higher soil moisture retention. Regarding the crops and the performance from the first harvest cycle of the potatoes planted under the agrivoltaic system and in the reference field, the agrivoltaic system was seen to have an 18.4% higher yield, and also from quality, the plant size under the APV system is greater than the reference yield, so more leaves, greater size of the actual crop, and the potato tubers were actually also generally larger. From the second harvest cycle, unfortunately, disease impacted the yield, so there was a 13% reduction in compared to the reference field. Whether that's a factor of the shading and the microclimate, that's yet to be seen by multiple cultivations of the potato. For the hydroponic system, it was housed in a greenhouse, standard greenhouse design, and the crops investigated was strawberry, tomato, and lettuce using 2 hydroponic techniques, nutrient film technique, where a pump is used to deliver fertilizer water to the grow tray, and a drain pipe to recycle the unused nutrient solution, and a substrate as a base for the tomatoes. Also, quite a number of benefits related to crop yield and reducing the water required to plant or cultivate the crops, so up to 85% water reduction. Just to make it quite quick, as time is going by quite fast, the hydroponic results were mainly based on the performance of the crops. So in short, from the crops that were grown, there was evidence of good yields in some cases, and also especially for the strawberry and the lettuce and tomato as well. And I think the main takeaway from that is that the hydroponic technology is quite well documented and known that it does save water. So the yields weren't too badly impacted by the technologies applied. Lastly, in conclusion, the key takeaways we can get from this. So like I say, I'm mainly focused on agrivoltaic, so sorry if this is agrivoltaic heavy, but we have seen from the example that I presented and from this diagram on the right that agrivoltaics do offer multiple opportunities to address each area of the water, energy, food ecosystem nexus. So from the use of the energy to integrating water management solutions, protecting crops through modules over the crops, or changing the microclimate to have some shading aspect through the shading aspect. We expect that semi-arid and arid environments, water-scarce regions are expected to benefit more from the shading. As you can imagine, under those high heat stress conditions, shading might actually be more beneficial even for crops that aren't normally shade tolerant. So crop performance, as you saw in both systems, hydroponics and agrivoltaics, may be enhanced. And yeah, as I mentioned, hydroponic water saving capabilities are well documented. And lastly, through what we try to do, coupling technologies for resource efficiency and multiplication of benefits. So if you can just imagine quickly the energy from an agrivoltaic system being used to pump and filter the water for the hydroponic system and also for the agrivoltaic agricultural activity. Yeah, and thank you for your time, and I will be available for more questions later.
Thank you very much, Brendan, for this interesting presentation. It is now time to move to the third theme of this session. It is dedicated to the sustainable water management decision support tools, and the first speaker will be Vicente Martinez Lopez from the Spanish National Research Agency in Spain. And is also a member of the WaterMed project. Vicente, please.
Okay, can you see? Thank you, Célia. Can you see the screen?
Yes, we can.
Okay.
Thank you.
Okay. The title of this presentation is the Assessment of Smart Agricultural Tools for Efficient Water and Fertilizer Use. There are several tools for inefficient management of the use of water and fertilizer in small agriculture. We are going to mention some of the most relevant and how WaterMed platform use some of these tools to plan fertilization. In this slide is shown some tools normally used in a smart agriculture for fertilization. A brief description of this tool are the data acquisition is the first tools were devised with IoT technology that collect valuable crops information. Some examples are a soil sensor, can measure moisture, salinity, soil temperature, that give us information about the root environment. Also, water and CO2 sensor will give us information about transpiration plan, for example, in greenhouses. There are also drone and satellites with multi-spectral and hyperspectral cameras. This device can provide information to calculate several agronomic indices. We can obtain information about crop water with MSI, moisture stress index, normalized different water index, NDVI, normalized different vegetation index, the Cariosavi, chlorophyll absorption reflectance index, and soil adjusted vegetation index. New telecommunication technologies such as 5G, Wi-Fi, API, next generation service interface, geographic information system, or global positioning system offer interesting possibility to interconnect different sources of information. The development of this technology entails the accumulation of large database that must be stored for its management. In this sense, big data tools allow us to process a large set of data to get information and knowledge about crops development and crops behavior. Blockchain agriculture enables the traceability of information in the food supply chain to improve food safety. It's necessary to obtain this large amount of data to use artificial intelligence, machine learning, or modeling. Based on the acquired knowledge, we will be able to send orders to the actuators to apply water and fertilizer in the appropriate concentration and doses, system that can perform the required function after the compilation of the collected data. A spectacular advance is in the area of robotics. there are robotic systems capable detecting different areas for plot-specific irrigation or fertilization needs. This robot also can decide when and how apply the relevant doses and precision. WATERMED platform use several of these described tools to offer a fertilization advisory service with high precision. The objective of the platform is to be functional, regardless of the level of modernization of the plot. A farmer who does not have a great technology deployment can obtain precise fertilization program based on the characteristics of the plot and some meteorological data. In the same way, a farmer who has technological device deployed on the plot can manage and control them through the WATERMED platform. This is possible thanks to the incorporation of data acquisition, connectivity, and communication technology like edge computing, data modeling, and web tools for communication with actuators on the plot. The first step will be the introduction of the WATERMED platform uses several of these tools to offer a fertilization advisory service with precision. The objective data acquisition is this one. Okay. The objective of the platform is to be functional regardless to the level of modernization of the plot. A farmer who does not have a great technology can, default. The first step will be introducing the agronomic data by the user about the crops, plantation, frame, soil, and water analysis irrigation system. Next step will be incorporated on meteorological data. This data can be obtained from public weather station. Weather station is tailored in the plot, or from services such as WeatherBit with acclimated data network with API technology, etc. In addition, the platform incorporates data collected from Sentinel-2 satellites. Values of agronomic index associated with the plot are shown. And finally, data can also acquire from IoT device deployment on the plot, such as soil measure, sensor, water meters, and conductivity meters. The communication and data interpretation system used in WATERMED allows a fast, robust management on the data acquired in the monitoring system. For the development of irrigation algorithms, all the parameters that can affect water needs of the crops have been taken into account. In this way, the influence of parameters such as soil texture, shade area, plantation frame, efficiency of irrigation system, or the phenological stage of the crops was taken into account to calculate evapotranspiration of the crops. And by evapotranspiration, the water that disappears from the crops by the process of plant transpiration or evaporation from soil. For the calculation of fertilization, algorithms were developed taking into account both crops' nutritional needs and the current nutritional status of the crops, obtained from water, soil, and plant analysis. An algorithm was designed to be able to calculate An algorithm was designed to be able of calculating the appropriate doses and frequency of irrigation for each type of crops. In similar way, it is shown a fragment of the decision tree of the fertilization algorithms where both the nutritional requirement of the crops and the availability of fertilizer from a farmer are taken into account by the platform. The result of this process is the obtaining of irrigation and fertilization plan that the user can apply to his crop. If the user has the appropriate facility in the plot, they can manage fertilization rules through the platform. Specifically, in the case of irrigation, the platform will show the total volume of water for the plot for each irrigation, the number of irrigation per day, and the irrigation time. Very useful for timed irrigation programs. In the case of fertilization, the platform will show an adjustment of the nutritional needs and a distribution schedule with the dose of commercial fertilizer available on the user plot. The platform converts the fertilizer units, nitrogen, phosphorus, potassium, etc., in kilograms of commercial fertilizer per hectare. To finish this presentation, I would like to show some results from one of the pilot plots in Spain, after following platform recommendation. In this example, irrigation management through the WATERMED platform of a cherry crops in a pilot plot in Vienna, Spain. It allowed a water saving of approximately 25% compared with traditional management. This water saving did not affect yield, which remained similar to the control of the traditional management. Therefore, following the platform recommendation, increase water use efficiency.
Vicente, could you please conclude?
Yes. In another
running out of time.
In this is the last one. In another pilot plot, we can see the saving of fertilizer following the recommendation of the platform. Is about 14% of nitrogen, 12% of phosphorus, and 8% of potassium. Okay, thank you for your attention.
Thank you very much. Thank you very much, Vicente. It is now to move to the other speaker, Aparna Shadrinskar from the Technical University of Dresden, and she is a member of the DSWAP consortium. Aparna?
I will be talking about the decision support framework that was developed in the TU Dresden, and this is done under the scope of the DSWAP project. So to start off, I will start with a little background on why we are doing this. So the objective, of course, is because of increased water shortages, which is triggered by both population growth as well as increasing climate change. There is an increasing need for fresh water in the world. Particularly, as you can see in this figure, in Europe, specifically the situation, many countries are under high to moderate water stress. And this has necessitated freshwater resources, alternate freshwater resources. Since agriculture accounts for almost 70% of the freshwater withdrawals, replacing this by treated wastewater reuse can be a very useful resource, not just reducing on the energy costs, but also increasing the nutrient content that is available to crops. However, when we are talking about reusing treated wastewater, we must consider the risks of spreading of biological as well as chemical contaminants of emerging concern to the plants, to the various parts, specifically the roots, which are also consumed, fruits, as well as leaves. And we must understand if we must have an idea of what water quality must be used for irrigation in order to reduce the risk for or eliminate risks for human consumption. Furthermore, there is a lack of unified water quality standards for wastewater reuse in Europe. In this context, the objective of our work here was to first evaluate the current state of the art, particularly the scientific literature on the performance of various secondary and tertiary treatment technologies. Furthermore, also understanding which conditions are important to increase the or which conditions are beneficial and increase the performance of removal performance of for these biological as well as chemical contaminants. We have presented we wanted to present public data sets publicly using a web service, as well as have a preliminary comparison or a high-level overview on which treatment technologies suit which kind of contaminants or for the removal of which contaminants. So the basis of our work was an entity relationship diagram, where we have broadly contaminant groups as well as technology groups. Then we entered the contaminants and the technologies which are particularly of concern in the project, as well as which are sort of more important for this kind of wastewater reuse. We also include information on the water source, so whether it's a primary treated wastewater, which location this particular place in, because these factors could also play into how the performance or the removal of the contaminants. So the water source as well as the conditions. And when it comes to conditions, it's both the conditions of the technology, so basically the temperature on which the temperature of the reactor, or sort of in the case of membrane technologies, the size, as well as orientation and these things, as well as water quality parameters like pH or biological oxygen demand, as well as total suspended solids. And all of this was combined to form various cases. Now, all of this information, including the contaminants and the cases, were then used to store values of the performances or the efficiencies. Therefore, we have a wide array of information available. Therefore, when we evaluate or when we understand the efficiency values, we can also understand what conditions or what are the treatment conditions that are leading into this. I'll just show you briefly on how this particular web service works. So as you can see, currently it has data from scientific literature on both chemical as well as biological contaminants, and also secondary and tertiary treatment technologies. For the chemical contaminants, we evaluated the performance using percentage removal efficiency, for biological as log removal values. The high-level summaries present also the number of records, so a user can already understand how much data is available. For bacterial contaminants, we have resistant bacteria, total bacteria, fecal coliforms, as well as E. coli, which are important water quality indicators. As for the chemical compounds, there are many compounds available, but today I will talk about carbamazepine and sulfamethoxazole. And we also have a wide number of genetic markers important for antibiotic resistance spread. Today, I'll talk about class 1 integrons and 16S rRNA. While we can filter the records by the contaminants, we can also filter it by the technology groups. So what are the amount of data available? So for the secondary today, I will talk about conventional activated sludge treatment. The tertiary, I will talk about ozonation as well as UV combined with H2O2, so disinfection and oxidation modules. We can also, so a user can already see the ranges available for a particular treatment technology. Like in the case of conventional activated sludge treatment, you can see that for these particular chemicals, you have high removal values, but there are also large ranges available in certain conditions. Similar in this disinfection module with respect to ozonation, you have high removal efficiencies, but also large ranges, particularly for carbamazepine, while sulfamethoxazole shows relatively lower ranges of removal. The oxidation treatment performed quite well, and we can see a good amount of removal within the data available. But of course, again, like I said, the conditions are also important. You can also filter it out by technology groups, and in general, we see osmosis and oxidation modules perform well for the removal of chemical compounds of carbamazepine, as well as sulfamethoxazole. Here we see reverse osmosis performs really well for the 12 cases obtained, as well as disinfection and oxidation. Moving on to the genetic elements for the class 1 integrons, we see osmosis performs quite well, as well as disinfection. Membrane bioreactor also showed a good performance for the removal of these, with more than 4 log removal for certain conditions. UV treatment, conventional activated sludge and Fenton treatment was good for 16S rRNA, but however, we must note these ranges. The final view is a tabular view for users who want to get into the details of how these treatment conditions or these high treat performances were obtained. So we can filter out, like you can see, we can just type out the treatment interested in and the values you're interested in and understand. So here you can also see the links to the studies from which these values were obtained, and you can already get an overview on how these performances are and look into a more detailed view on what conditions were used to obtain this. For the chemical contaminants, we put in sulfur methoxazole and carbamazepine, and for the same treatment technologies. And of course, now we can put the percentage removal efficiencies, and then we can already see what conditions or what studies are relating to this and how these conditions were obtained, and a user can possibly replicate these conditions. We're still working on a more expert view where you can download the data sets for people interested in it. So this is the overview of the decision support tool with the current state of the art. Some primary conclusions which were obtained from this particular decision support module was, for the chemical contaminants in general, it was seen that oxidation and disinfection modules, most of the cases gave good performance removal. So this, the green indicates performance of greater than 90% or removal of greater than 90% for at least 3 to 5 cases. Yeah. For the biological components, we see that secondary treatment is sometimes sufficient. However, a disinfection module, of course, gives you a better treatment. And I remember someone saying this before, that in Germany and Switzerland, they've already upgraded the wastewater treatment plants to include disinfection as well as oxidation modules. And I think this result also gives you, sort of supports this, saying that upgradation of wastewater treatment plants with disinfection or tertiary treatment modules could improve the wastewater quality, particularly for irrigation. Yeah. So thank you all for your attention, and please type your questions in the chat and I'll be happy to answer it.
Thank you very much, Aparna. It's now time to move to the last talk from Özlem Karan Özgun.
I've been developing the simulation platform for the integration and modeling of water treatment solutions in our FIT4REUSE project. And I am Özlem Karahan Özgün. You have pronounced it perfectly well. From ITU Nova, the Technology Transfer Office of Istanbul Technical University. I'm going to make it brief so that we can catch up with time. So why do we need the simulation platform? What we thought was that we were going to, do a lot of experiments, but replicating them would, of course, need a lot of challenge for everywhere in the Mediterranean. And we know that the simulation platforms are proved to be really effective tools to mimic the performance of the real systems. And therefore, what we did was we designed a simplified simulation model for the FIT4REUSE solutions that we have been working on, that our colleagues have been working on in the field or in the lab, and to use this tool for decision making in order to support the decision making for the applied solutions for non-conventional water resources. Basically, the idea is to try to simplify it as much as possible, because we know that there are really very good models that are able to simulate the treatment systems. But usually those models are quite complicated, especially for the users. If you're talking about users like treatment plant operators and or the farmers, for example, who would like to get some non-conventional water resources and seeking for solutions for that. So we try to keep it simplified and try to mimic it as mimic the FIT4REUSE solutions as well as possible with an easy-to-use simulation platform. Well, the main idea behind the simulation platform is that we would like to eventually come to the answer of the question, which configuration is the best fit for your purpose. Okay, so we know what the required treatment performances are in terms of conventional parameters, but what about the emerging pollutants, right? So, but what about the micropollutants in more general case? So this simulation platform could give you some answers about the treatment performances of conventional parameters together with the micropollutants of emerging concern, if you are interested in that. And we would also like to answer the question in a way to understand the cost of treatment in terms of energy and material consumption, and also about the carbon footprint of the operation that we're considering for non-conventional water resources. Therefore, this was the main idea to build this simulation platform, and the platform is really handy for the users, and it really has a user-friendly interface, easy to use. And what the platform does is that it is capable of simulating single units with simplified models, as I have already mentioned. But while you can simulate the single unit performances, you can also create some process trains which can be composed of different units together with the innovative enhancements that our colleagues are working on in the FIT4REUSE project. And so we can say that this platform is really suitable to generate different scenarios for different cases. So why do we need those different cases? As Aparna has already mentioned this very nicely, we have to define a specific case for each required solution. What is your non-conventional water resource? What type of pollutant parameters you have in that water resource? What is your target of water use? Are you going to generate a class A water or a class B? Or are you going to use it for aquifer recharge? Or are you going to discharge it to a reservoir, or use it directly for irrigation? So these are all making these different cases. So we have different requirements for different process trains that could be applicable. In addition, we have also the regional environmental conditions, as the climate, the temperature, and the different requirements for the crops, etc. And also, we still have some regional differences all around the Mediterranean for the regulatory compliance for wastewater reuse for irrigation. Therefore, it's really good to know how your treatment train will perform under the specific conditions in your specific case. That's how the simulation platform will be helping the users of the platform. And as I said, this has a really user-friendly graphical interface. And now I'm going to share you with my video about how to use the platform in some examples about what we have done. I hope you can now see it. No? Can you?
No.
It should be available now.
Yes, I see it, Özlem.
Okay, great.
Let's
So
try.
we basically have a very simple interface with all the units on the left, and then you just insert your data to the platform, your initial conditions, your system operating conditions, and then you just click the button and simulate and get the results in graphical form. And of course, you can also export them to Excel as data or any other tabulated form. You could, if you have some experimental results, you could use them to compare the model results with your experimental results and see if your assumptions about the parameters, calibration parameters of the model are correct. You have some graphical tools to zoom in to your graphics and move your graphics around, etc. This was an example from one of our wetlands, and this is another example from our one of our UASPs. And then you see this was calibrated for more than 400 days, and the model really gives good results in terms of conventional pollutants like the carbon, total nitrogen, and also phosphorus. So you can just see from one click of your simulation what your performance of your system will be even in the long term. Or you can zoom into for specific terms to get the performance of your system. It could provide data about the system performances for deciding on which process to use for better performances. This is an example.
I'm sorry, we should finish now. If you could summarize your final messages. This is really interesting.
Okay, yeah. I could just stop sharing this and then come to the simple conclusions. Like we could just reduce the need for specific case studies if we have an idea or using the simulation platform. One very important thing about this simulation platform is that we have developed this for FIT4REUSE solutions, but it is really expandable, and we could just add in the solutions generated from other Prima projects or from other experiences which could fit into the platform. So it is really, it could be easily developed further for many other applications and innovative solutions. And thank you very much for your attention.
Thank you, Özlem. We finished now this impressive overview of the project's contribution for sustainable water management in agriculture. I think that we had here many different aspects and different techniques and approaches that are being used. So this is really impressive. We don't have much time for the Q&A questions in the chat, but I think that most of them were answered while we were in the presentations. There's a question, I think it is for Aparna. How can we calculate the irrigation water quality index, since there are so many references in the literature? I don't know, Aparna, if you want to answer. And in the meanwhile, another question is for Özlem, if this platform will be accessible for farmers and stakeholders in other Mediterranean countries. This platform was really very, very promising. So many people will be interested for sure.
In regard with the first question, I can say something. Okay.
Okay. Thank you.
Okay. Okay. Salinity is a big problem, and there is different indexes and about the quality of water. Normally, the more spirit criterion is the salinity lab and Riverside classify the water quality depending on as a function of the electrical conductivity of the water. From the agronomic point of view, this is the index more accurate from the side if you want water, but it depends to the salt tolerance of the crops, because different crops have different salt tolerance. So not only we can use water of a certain quality that could kill some crops, and other crops are tolerant and do not affect the quality of the yield of the crops. So the water quality is a relative concept. Okay.
Okay.
Sorry, Célia, to step in. I just wanted to ask the other speakers if they can answer in the Q&A box in writing, because unfortunately, speakers from the next session have other commitments and we are a bit late. So sorry about that. Maybe we can use the Q&A box in writing. And I'm just wondering, do you think we should have just a couple-minute break or start immediately with the next one session?
Marco, maybe we can start.
Okay, yes.
Without break, because we are all online, so we can take our break when we want.
Okay,
so
I think you're right. Yeah, we'll ask for the participants just to be a bit patient, but they can go and grab like a glass of water in the meantime. Yeah. But I mean, I'll just give the floor back to Célia for concluding the session.
So I think the session is finished now. Thank you very much, all speakers, and the discussion can continue in the chat.
Now we give the floor to the moderator of the next session. That will be a roundtable discussion, to Alain Meyssonnier, President.
I will start. Okay.
The floor is yours.
Hello, everybody. I have the honor today to moderate the roundtable dedicated to barriers to sustainable water management in agriculture. My name is Alain Meyssonnier. I spent almost 40 years working in the water supply company of Marseille in the south of France as deputy general manager. It's a private company, subsidiary of Veolia Group. From July 2019, I am the elected president of Mediterraneen Water Institute, that we call IME, based in Marseille. The Institute has just celebrated its 40th anniversary in Valencia, Spain last week, with the presence of Prima. It is composed by 3 colleges, institutional and as ministers or region in charge of water resources and irrigation, private and public companies in charge of operating, and individual experts. It is the first water expert network in Mediterranean area. Little by its staff, but very big by its members and partners around Mediterranean to optimize the platform of good practices exchange for water resources, potable water, sewage services, irrigation and hydroelectricity. Uses through special meeting, webinars, and Mediterranean water forum every 3 years. Today, we have 3 experts for this roundtable. First of all, Caterina Cacciatori, who joined the Water and Marine Resources Unit at GRC ISPRA last year, excuse me. She's a trained environmental engineer in research in drinking water treatment at the University of Tokyo. but has furthermore obtained a Master of Arts in Environment Development and Peace at the University for Peace in Costa Rica. In the Water Quality Laboratory, she mainly supports the Citizens Engagement Project, the Gems of Water, supporting the work of the Social Engagement Platform of the World Water Quality Alliance in collaborating with the Global Environmental Monitoring System for Water of UNDP. Adriano Battilani, General Secretary of International Association Irrigants d'Europe, consulted and appointed representative by EU institutions and international organizations of Italian National Association of Land Protection and Irrigation Consortia, member of the board of the Euro-Mediterranean Irrigators Community, and leading scientist in charge of EU national and local projects funded by public bodies or private companies. And the last one, Professor Alke Jungver, who is currently Professor of Practice at Environmental and Resource Management Program at Arizona State University, member of Water Policy Group in Industry Flow at Australian River Institute. He serves as a senior advisor to Food and Agriculture Organization of the United Nations FAO and UNESCO, International Intergovernmental Hydrological Program. His public service career spanning over 3 decades. Dr. Jungver led FAO's water program and activities, UN Water's World Water Assessment Program and UNESCO Program Office on Global Water Assessment. He served as a Vice President of UN Water from 2018 to 2020. Well, my first question for all of you would be the following. In the previous presentation, very good ones, we had the chance to know about the outcome of 3 innovative climate projects. Which are your impressions? Well, thank you to concentrate to answer in 5 minutes each. Caterina, maybe you can answer first. And then Adriano and Professor Jungver. Caterina?
Yeah, thank you so much. So as you've heard, I'm not really the person responsible for water reuse thematic here at the JRC, but it was a pleasure to participate and to listen to the interesting presentations. And for my background and also for what I'm doing here at the JRC, I was particularly impressed in the importance that you've given to communication, and in particular when you mentioned that future research should also go into involving citizens and citizen science monitoring projects. And I was also quite impressed because the quintuple helix approach that you mentioned in one of the projects is also something that we are using. For instance, in the project that I'm guiding. So yeah, thank you so much, and it was very interesting to listen.
Thank you. Good morning, everybody. It was really interesting, not only following the presentation of this morning, but also to browse the website of the projects. There is a lot of good solution proposing hard and soft technology that can help the stakeholders and the farmers that irrigate using alternative water sources. So particularly, I was impressed about some, let's say, innovative approach to desalinization, namely the phytoremediation desalinization and DSWAP, the project DSWAP, that is, to me, energy and cost effective and also quite sustainable from the environmental point of view. All the topics that Luigi Rizzo has raised about the contaminant of emergence concern, and also Alain Leclerc were pointing out of great interest and will facilitate or say easy pave the way to reuse the water for farmers, and also the plant stress indicators. What is important is that these novel technologies will be scalable. It's important to point out scalability and applicability at the field level that might be safe for irrigation, and also analysis and tests of safety, productivity, and so on that are complementing the technological effectiveness of this technology. Is important whatever activity this group of projects is carrying on with respect to risk management. That is one of the threshold of we have to overcome in the next future also for the application of the rules of quality and so on, and the multi-stakeholder platforms. So also the use, the combination with fertigation and fertilization balance is quite important. My only concern, just to open a bit the discussion, is that again, we are having, as it was in the past for the decision support system, we have now a lot of platforms that are very effective in integrating inputs, but I'm afraid that they're not so effective to be integrated or to facilitate integration of outputs. And it's difficult for a manager, for a water agency to use all this platform for a specific topic or for a specific aspect of the multifaceted management of water use. So the problem is that we cannot access all the platform, although each of them is solving in a great way one aspect of the big problem. Thank you.
Thank you very much, Adriano. Well, Professor Unver?
Yes, thank you, Alain. Hi, everyone. First of all, it was very good and satisfying to see that the projects that I served as an evaluator way back are now bearing fruit and being successfully implemented, and they are reporting from their experiences. I am particularly impressed by the multidisciplinarity and the incorporation of multi-sectoral aspects into all three projects, and particularly regarding technology in its social, economic, and environmental aspects, incorporating risks, particularly, and understanding the environment within which these projects operate, and hopefully will continue to do so even after the projects are completed. One particular aspect that I was interested was the risk assessment done, and the stakeholder analysis and interactions developed in order to make the implementation more sustainable, and the incorporation of business aspects into the implementation. One point that I would like to make in the end is the issue and the opportunity of interoperability and interusability. Prima has been supporting a number of projects almost on continuous basis, all of which have been developing models, and I know that there is an emphasis on being interoperable, and I'm wishing that these projects will serve this particular purpose and contribute to accumulating the knowledge and making the knowledge available not only to their immediate constituents, but to the broader scientific and stakeholder communities. Thank you.
Well, thank you, Professor. Well, I just want to add that to add to your interpretation that IME is completely at the service of PRIMA to make the project possible. I mean, that is very important to bring together the scientists and the operators. And you should work together during the project, because at the end, maybe it's too soon for the project to be acceptable by operators, by farmers, by users, whatever, which is the final solution, the final use. So it's very important that during the process of the project, you get in touch with operators in the country you are working, and to see with them which is worth it, and how to maybe reorient some of the solution. And the other thing in that IME is working with World Water Council on behalf of the World Water Council to create the worldwide observatory for non-conventional water resources and renewable energy dedicated to these water resources. And and we are working from now to 2024 to prepare the condition for this observatory as a pilot zone in the Mediterranean Sahel region. And I think it will be very interesting for us to integrate all the results of this works we are doing and financed by PRIMA in the observatory. Like this, we can use it maybe better in the future. But the next answer, second answer, would be how important is the role of water policies and governance to achieve a more sustainable water management? Well, we'll ask first to this question. Maybe you, Professor?
Yes, thank you. Again, PRIMA has to be congratulated for incorporating water governance in its projects as almost a basic requirement. And I see that water governance is adequately embedded in the projects. Again, for the success of the individual projects, but for their sustainability and uptake by the stakeholders, local communities, and the public and private partners in the respective communities. Governance aspects are extremely important. And governance means many things, but in this particular context, it's the processes through which public and private actors identify their priorities, their preferences, and implement those and monitor and enforce those decisions. And we have to keep in mind that the major audience, farmers, represent the private sector, but they do it in a very grassroots manner. And it's very important to understand the governance aspects involved in this. I would like to come back to that in a couple of minutes, but I would like to indicate the importance of stakeholders in the broader governance issues, particularly in the south of the Mediterranean, where governance structures are not as uniform or regulated or pretty much expanded to the whole communities as they are in the European part of the Mediterranean. In this context, it's very important to have the public institutions and the broader stakeholder communities to interact in whatever multi-stakeholder platforms that are available, given that water policy operates within the confines of the broader governance structures in a country. And in many cases, those broader governance structures are more limiting than liberating. And as a result, if we don't take that into account adequately, then that might be a barrier to otherwise a wonderful solution or a combination of solutions brought to solve a problem. And with this, I would like to end by saying that water policies are seldom standalone policies. They are a part of or interact with food security policies, food sovereignty policies, energy, disaster risk reduction and emergency policies, public health policies, poverty reduction, and last but not the least, environmental and climate change policies. And we have to make sure that the way we design and implement our projects and make them lasting beyond the completion of the project will depend on the success of these policies to be coordinated. And again, this is an outcome of the governance system, and rather than trying to impose our perspective of how governance should be, we have to understand how the governance is operating and how pragmatically it could be gradually improved through a project in order to make the benefits of the project longer lasting. Thank you.
Thank you, Professor Unver. And Adriano, what's your position about the governance?
Well, okay, governance for us is strictly linked to policies. Policies that, being ruled, are an irremissible enabler for whatever kind of governance that is linked to finance. When you have to deal with infrastructure, when you have to deal with business, your investments are driven by the possibility that the policy open to the government. So we are now, let's say, pushed in a way to implement more water use by the regulation 741/2020 of the European Commission. But we have to look of the possibility that are offered with the revision of many other policies that will impact heavily on all the governance of the sector, of the broad sector of water, starting from the utilities till the farmers and the irrigation communities. So let's say we can talk about the discussions that are ongoing about the revision of the guideline of drought and disaster management of the river basin. What is happening in terms of water reuse treatment directive, the drinkable water directive, the energy efficiency directive are all enablers for our governance. On the other hand, good policies have to take into account the rigidity of the infrastructures. Existing infrastructures cannot be modified in the short time span that often the policy are indicating. It's ambitious to have good policies to increase sustainability, but the reality is clashing with the rigidity of the infrastructure. We have infrastructure that cannot be easily modified, or in many cases cannot be modified at all. Or we have made investments mainly in modernization of the irrigation system in many countries that have a return of investment in a mortgage time of more than 20 years, and we cannot modify now again before the end of its investment period. So these are real barriers that in many cases policy don't know or don't consider. So when we have to land the policy dictate on the idea of into a real governance, what we are suggesting is to start considering the infrastructural context and the real economic context. So we are doing our best. It means that we are adapting and we are using all the opportunities for investments, and we are pushing the bureaucracy to remove the barrier that in many cases they are imposing as a consequence of a local or national interpretation of the European policies and indication. Thank you.
Thank you, Adriano. I completely agree with you. Well, Caterina, what is your position?
Well, obviously, we believe that water policies are very important, and in case of the water reuse regulation, they have it enabled homogenization or the creation of common practices around risk assessment and water reuse. And this needs to be, as you were saying, Adriano, I guess, flexible enough and adaptable so that both member states that were already implementing can follow, but also new member states can easily adapt and implement according to the local context. And in this sense, I think the importance of water policy and the Water Framework Directive, for example, is the push for participation that should be enhanced even more. And this was very important also in the development itself of the guidance, for example, through consultations, working groups, and this allows for the water policies to understand what are the challenges on the ground and the needs, because of course it's very difficult among member states, and we believe that in the guidance, for example, through the use of the case studies, this was partly possible to address and at least include different aspects, different way that different parts of the risk assessment have been implemented in Europe.
Well, thank you very much, Caterina. Well, I just added that in the themes of governance, okay, we have policies, we have politics, we have vision, but we have also governance on the field. And the governance on the field, we don't have to forget that. We need to sensibilize, we need to train all the stakeholders if we want to succeed. And this is the key answer to this question. And by the way, in IME, we have just produced a methodological guide for reuse project at your disposal. It's in French, English, and Arabic. And so this document is public now, and so if you need it, please, we will send it to Prima, and then you can take it. It's based in our experience of operators, different operators from Tunisia and France, and based in different projects we have done in Tunisia about reuse. So with experience, good one and bad one. And so this is we decided to make this guide to DD public. So the third question would be the following: which are, in your opinion, the most influential factors for the successful implementation of water solutions in agriculture? First, Professor, please.
Yes, Thank you. I would like to touch upon two factors or two reasons for success. One is active multi-stakeholder involvement, and the other one is understanding the motives of our major clients or the users. And for the second one, I would like to talk a little bit about the duality between water use efficiency and productivity. First of all, in terms of stakeholder involvement, engagement, again, from a PRIMA perspective, we are looking at the northern and the southern segments of the Mediterranean, and we see two different pictures. And it's important to understand the differences between these pictures in order to make our projects successful in all Mediterranean circumstances. And I'm not referring to climatic differences. I'm referring to the differences in stakeholder engagement, which should take into account the cultures. And by cultures, I'm referring to the cultures of the groups, of the stakeholders, but also the differences in institutional cultures. In a given country setting and in a given government setting, different institutions may have different cultures, and that may have a big impact on the success of water management and related projects. I would like to refer to a survey and a global report that Water Policy Group conducted and published last year with input from 88 countries from around the world. We polled the water leaders, the ministers, water ministers, and the heads of water agencies, and asked them what the highest risks they perceived in terms of their objectives. And an overwhelming majority listed climate change as the top risk, followed by increasing demand, floods, and droughts. And all of these are beyond the confines of a water minister. Then in terms of challenges, they responded and they were given over 10 options. Again, the overwhelming response was a lack of integration and prioritization of water issues in government policies. And here we are looking at the government as the big stakeholder in a complicated picture. And even the water minister is feeling sort of outside the main control panel, impacted by factors that are outside his realm, and also not really being able to influence the policies. And if we go down to the stakeholder level, within the framework of an FAO project, we looked at the stakeholder perceptions, and that was similar to the south of Mediterranean conditions. And it was striking to see that government institutions did not see the barriers to active stakeholder engagement in water resources management. And on the other hand, stakeholders themselves, the non-state actors, indicated that there were barriers, and those barriers were basically emanating from a lack of transparency, lack of data and information, and lack of concrete policies for stakeholder engagement. So with this type of setting, it's, for a project that is intending to change the paradigm or to install a new perspective using technology, but also social sciences, economics, environmental sciences, etc. It's very important to understand these these dualities that exist that will have to play out in the implementation and beyond. And here I would like to come to the farmer motives in adapting technologies or new systems, new management approaches. The major motive for a farmer is the risk perception, followed by the profits, the farm income, and a little bit yield and somewhat productivity, and definitely not water use efficiency, unless water is totally prohibitive in a setting, which is seldom the case. Again, south of the Mediterranean, water scarcity is an issue, but the farmers will use that in their risk assessment, but in adapting new technologies, they will look at best, productivity aspects and not water use efficiencies. And this is important because anything that we save using better technology in terms of water, then will have to be accounted, either going back to the environment or for improving the water use efficiencies in other sectors than agriculture. And we have seen examples even in developed country settings, such as in Australia or in Spain, where farmers were resistant to water saving technologies. And even when they accepted to adopt them, they wanted to use the water saved rather than having it reallocated to another purpose. And I think this is important to understand to make sure that our projects are realistic and therefore they will not be prevented from implementing what they intend at the beginning because of a misunderstanding of the user motives and priorities. Thank you.
Thank you, Professor. Well, Adriano, what is your opinion?
Well, let's say water solution doesn't exist as such. There is no water solution that we can say is one size for all, but we have also to look for the water solutions that are responding to local conditions, particularly to crop and soil husbandry and to the local environmental needs. These three drivers are deciding what are the viable water solutions we can apply as stakeholder or agricultural water manager. And if we go for the crops, for instance, many discussions, they are asking us to support farmers in changing their crops. It's not possible as far as there is no market, there is no distribution chain, there is no storage system for the products because the market is not made to be accessible by the single farmers that have to change the crop. So it's a system that has to change in order to facilitate this step. Then when we are changing crops, I was, let's say, a bit hurt in a meeting in Europe I got a couple of weeks ago when they were defining farmers as price taker. So farmers is cropping and then is selling at the market price. It's not the reality. Farmers are subjected to quite strict and not so, let's say, so beneficial, so profitable contract with big companies. So they have to deliver in time a defined quality of a defined quantity. And in this case, the only water solution that is viable for them is the one that is performing like a kind of insurance and reducing the risk that they have to pay penalties for the quality and the quantity of products they cannot deliver. And this is also the reason, because as mentioned before, water savings are normally kept inside the farming sector. Why? If you are investing in technologies or in strategies, or you are working in order to save water, this investment must pay back itself. Otherwise, is a burden, an economic burden for the farmers that is producing benefit for other sectors or for the broad society. So is likely to have a kind of hidden taxes that you have to pay. In many cases, they are claiming that farmers are subsidized by common agricultural policies. That is not really true. Getting back in the history, is not a subsidy, but is a compensation. The compensation of what? Of the inelasticity of the prices with respect to the cost of production. Farmers are the only that cannot increase the price of the product they are selling according to the increase of the cost. And this is a particular dramatic problem in this moment in which we are suffering for the high cost of the energy and all the energy demanding products we are using as input. So the water solution must take into account that it must be energy efficient, viable, economically sustainable, but also that does to take into account that is something that we can introduce as ecosystem services, and unfortunately, ecosystem services are not rewarded to farmers. So it's a kind of vicious loop. One of the best enablers to have effective water solution is to move from the rewarding of the investment from the price of the products that is inelastic to the ecosystem services and pay for the common goods agriculture is producing. That's the kind of water solution we can accept. In this way, there will be money for investment, a risk perception, and that correctly, it was mentioned before, that is more close to the need of the farmers, that they will perceive this action as viable, economically sustainable, and also profitable at the end.
Thank you very much, Adriano, and thank you to remind us the basis of the agriculture, which is very important, because we always say that the agriculture is the first consumer with 80% of the water resource using. And so, but it's not so easy to change the things. And we have to speak with the agriculture. We have they should be part of the solution. They should be part of the solution. And there is very good example in Israel, in the south of Spain. Sometimes it doesn't work, but most of the time it's work when you speak with them, when they are part of the solution, when you explain from the beginning what is a problem. So they agree, and sometimes they propose solution better than you imagine. And so this is the other thing, is that we are in the Mediterranean, and we have north and south and east. And tomorrow, maybe, I am quite sure that the south will be better than the north, and the solution will be coming from the south to the north. If I would be a young engineer now, and I'm very interested in the technology of reuse, of technology of desalinization, of technology of optimization of the process, I will be starting my working life in the south, not in the north. In the north for the technology, yes, of course. And you are a very, very good example, everybody, today. But in the south, we have the experience of the field, the experience of the agricultural reaction, the experience of the reality of the economy. So maybe tomorrow the cooperation will be south to north. In the north, we just began to understand what are the climate change conditions. In the south, the climate change is something more. There is something new, but they are really acclimated to the first problems for water, facing the water resource, which is demography. Climate change is something added to the demography. In Europe, we don't have problem of demography, but now we have problem of climate change, starting by France. One, we could following a long time. Catherine, what's your opinion?
So I want to attach to what Professor Anver mentioned. So the good communication of the stakeholders, and so all of the stakeholders, so farmers, consumers, water treatment plants, operators, and the institutions. And this is again linked to the governance and to what are the potential obstacles through, for example, bureaucracy that is also different in each country, and this could be hindering factor to the to successful implementation of water reuse, for instance. And then at the source, I would also say water quality. So, and this is linked to technology. For the implementation of water reuse successfully and to respect the requirements that the regulation sets, there needs to be a certain water quality at the source, and this requires that that the technology is available and it is scalable and it is applicable, and this is also again linked to the financial aspects. And another element could be also water quantity, because in those countries where maybe there is no issues linked to water scarcity, the implementation of water reuse will be slower. So this is also an aspect that needs to be accounted for and can be addressed looking at the elements, for example, of local cultures, and building this trust also through communication, and being able to communicate the benefits that are in water reuse.
Okay, thank you very much, Caterina. And maybe to conclude our roundtable, maybe not the last question, but 1 or 2 minutes for each of you to say to tell us what will be your main message to the assistants of today, contrary to the barrier to sustainable water management in agriculture. Professor?
Yes, I guess my message will be a summary of what I said. I think the active stakeholder engagement is the key to the success of any intervention in water management, and understanding stakeholders is as important as, if not more important, than implementing the right technological solutions and integrating different disciplines into a package of solutions. So understanding stakeholders, stakeholder engagement, both at state and non-state levels, and also at the decision-making versus implementation levels is key to the success and the sustainability of any intervention. Thank you.
Adriano? Excuse me, I was mute.
Okay, I fully agree with Professor Unver that stakeholder engagement is the key, and we are always asking for an early stage and equal footing engagement, because in many cases we are consulted at the end when the products are structured, the idea are developed, and then we are just asked if we like it or not. Participation is something different than consultation. So stakeholders must be engaged at the very early stage of each project and keep engaged till the end in order to be useful for new technology, providing the idea for new technology applicability and so on. Another point is that we need novel market to support novel businesses. Just to propose idea to change the businesses is not creating the markets. Again, is a vicious loop. The same citizens that are asking for a better environment, for less pollution and so on, are those that at the market, at the supermarket, are buying only the high quality fruits, perfect in shape, perfect in color, that they don't know, unfortunately, that represent less than 25–30% of the overall production. It is the only production that is paid for the farmers in a profitable way. So we have to produce 100% to sell 30%. This is a way to use and waste water, nutrient, energy, and opportunities. Another point is remove the bureaucratic barrier and facilitate the, let's say, the ownership of the stakeholders, of the territories, of the river basin and whatever. Farmers were having a stewardship of the territories since 20 or 30 years ago. Then they lost grip on these stewardships and they lost the contact with the territories. So they must be invited again to be responsible of the land that is the main capitals of our enterprises.
Thank you, Adriano. I'm sure that Prima will be register all this and deliver it after. Caterina, what's your last message, please?
I'm also in agreement fully with Enver and Adriano on the importance of engagement of different stakeholders, and I would also extend it to the whole society. I'm happy to say and to see in my short experience at the Commission that there's a big work that is being done, and I'm familiar with the water sector towards communication of science and involvement of citizens. And even in my experience, for example, in the World Water Quality Alliance, it's been recognized that the social engagement is essential to address water quality issues. So I'm really glad to hear that this is also as main take of water reuse. Thank you.
Well, thank you very much to you three, and as I told you, all this was registered, so we could listen it more in the future. Though I just want to tell you that IOME is also preparing with a Union for Mediterranean and the Tunisian government through the Ministry of Agriculture, the 5th Mediterranean Water Forum that will take place in Tunis in January 2024. And we can ensure you and Prima Foundation that we will invite you all to participate and collaborate to these 3 projects. And well, thank you for your participation to this roundtable. Now I would like to introduce to you Mr. Vangelis Constantianos, excuse me, Regional Coordinator and Executive Secretary of the Global Water Partnership Mediterranean. Vangelis is also a partner of the WIF4REUSE project, aiming to develop a Medwater energy food ecosystem community of practice and a very good friend of IMA. Vangelis, the floor is yours, and thank you all.
Absolutely. Dear Alain, thank you very much for your introduction. Dear colleagues, it is really a pleasure to join this webinar, and sincere thanks to Prima for allowing for this promo, I should say, of the incoming project WIFI4MED, Water, Energy, Food Ecosystem Nexus for MED. I'm really impressed on the volume, on the width and the depth of the information that has been shared. And you will see in the very short presentation that I have and I will share with you, that is in the very heart of this upcoming project. Do you see my screen? Please let me know.
Yes.
Okay, so this is an upcoming project, a CSA of Prima, that looks into developing a community of practice on the Wi-Fi nexus, a subject that has come up in many ways over your discussions and the presentation, especially in the panel. And thank you, Professor Olcay, for bringing up the importance of making these linkages, the interlinkages. The origin of the project comes from a major conference that organized a year back, last September, and that was on the Nexus Science Advances, organized by the Commission, Prima, the Union for the Mediterranean, and the Cyprus Institute, bringing together policymakers and practitioners, projects, including, of course, of Prima, and bringing up the importance of integrating further all the Nexus sectors in order to work together towards sustainability. One of the key findings of the conference was that there has to be a platform that will facilitate this stakeholder alignment of all Nexus sectors, and Prima took it up in a very fast way, and here we are a year after having a project that is ready to be launched. The rationale of the project comes from the understanding or the recognition that sectors currently, the water, the energy, the food, the ecosystems under the climate conditions, work in silos, no matter the efforts that are taking place for more than a decade in different parts of the world, and definitely in the Mediterranean, being a test case for the Nexus. And here we are under a particularly strange conditions, I should say, with an energy crisis that is reflected definitely to the economy, the very hard way, with a food security challenge that seems to be coming up strongly in different parts of the world, including Africa, hopefully a bit less in the Mediterranean, but we're going to see that also in our neighborhood eventually. And definitely the climate change impacts that have as major victim also the ecosystems along with the economy. So this makes a really explosive mixture that demands today, not tomorrow, the closer integration, alignment, and work together of the sectors. And here is where this small project comes in with its limited capacity, but its strategic or catalytic ambition to bring together in a structured way these different sectors to provide a platform on which all partners will be able to get together and exchange on solutions. And here is where we get to your major point, the major point of the panel on the stakeholder engagement. So provide structure of the stakeholder engagement, and at the same time going into depth on demo sites where Nexus applications have taken place or will take place over the life of this project. The three projects that came together in this webinar are definitely very close to the rationale of the Nexus upcoming community, and we will be looking also for other demonstration sites from Prima, from the Horizon 2020 projects, but other projects around the Mediterranean or processes around the Mediterranean that can join. This comes in an excellent moment where the European Green Deal has embarked. The Union for the Mediterranean with the Water Agenda provides a solid background for development of tools and policy instruments. And here is where we can get the policy, the science, the policy, and the practice together. These are the key objectives of the projects: identify the solutions, engage the policymakers and the stakeholders, go deeper into the regional demonstration sites. This is the consortium of the partners that has come together. You will identify several networks of water stakeholders, but also energy stakeholders and agriculture stakeholders that are getting that are joining forces in the consortium. But the consortium is only the core of the partnership. We look forward to close collaboration with all the programs, including and organizations, including, of course, IME and the upcoming observatory on the non-conventional water resources and energy, and all those out there that have a role, that have an intention, and that have a will to work together for finding the solutions. So you will be hearing more about the project, and hopefully this will be a line where we can get together and work together. Thank you very much. Let me pass it to the organizers again of the three projects that have brought the webinar together, and with sincere thanks for this opportunity.
Thank you so much, Vangelis. Very interesting, and I believe that it is another great opportunities for all of us founded by Prima. So we have to say thank again to Prima for all the initiative they are performing. We started with the first call, as I said at the start of this day, and I believe that looking at the presentation of all the three projects, this is a very, in my opinion, for sure, a very clear signals about the quality and the quantity of all the consortia are able to do within this framework of Prima Foundation. And I believe that the main reason about this is that the Prima Foundation centered a link between topics and is focusing in a specific tailored area, so the Mediterranean, where all these interlink between water, farming systems, food production, and food systems is very crucial. Is very crucial since a lot of time, but is very crucial now for several things. Of course, the climate change. You know that the Mediterranean is one of the, I guess, hotspot of climate change. The food crisis due to the war, and the water scarcity. We suffered this year particularly, but we will have more and more frequent events of drought and water scarcity. So I think that the entire program Prima is very relevant for all the researchers, the companies, and the water operators that is working on this topic. And so I would like only to finish, to close with the other coordinators, this event saying thanks a lot to, for sure, all the participants. They have seen very numerous, so thanks. And thanks to the other the colleagues of FIT4REUSE, for sure, and the colleagues of the other two projects, the twin projects, because we did, in my opinion, a very good job. And also thank again for the organization, a specific person who are engaged about this, Viola, Stevo, Marco, Sara. And final thanks again to Prima that supported us. And I believe as a researcher that this kind of events, so where three or more projects funded on the same topic, on the same call, are not so usual. And I believe that even in this case, the specific attention of Prima and of all of us could be a real added value, because it is strange, in my opinion, in my expertise, to have such a big event on of course, with a clear planning about this, where all the elements have been integrated. So I'm very happy about this webinar, and I hope we go on again with this integration and collaboration. Thank you so much. I leave the floor to Eddie, the coordinator of DSWAP, and then the coordinator of WaterMed 4.0. And then Marco, because Marco has to close.
Yes. So first of all, Attilio, I'd like to thank you and your group and the FIT4REUSE group for this initiation. I think one of the most important things dealing with water reuse and the whole nexus of going from technology to practice is to be able to share data and share knowledge. And I think this was a wonderful opportunity to do that. I think hopefully it will be just the beginning of networking, as Marco likes to say, and pushing specific topics forward, either on a large, network as we see here, or on smaller, specific networks that can deal with questions that are related to both water quality, food security, and of course, environment, as mentioned here. And I think, as was mentioned, we need to also see how best to translate all of the data that's generated in these projects to a language that can be understood by both the policymakers and especially the farmers and the people who are actually with boots on the ground, as they say. And again, I'd like to thank everybody for being here and hope that it's just the beginning of communication that can be facilitated for more productive networking and policy and practice in the future. Thank you very much.
Thank you. I would like to finish this webinar with first of all, thanks to the organization, all the partners in the 3 PRIMA project. I think that, as my colleague said, that it's a very good forum to share acknowledgement, opinion, etc. And I would like to finalize with, for example, I think that we agree, all of the, or most of the speakers, that the stakeholder engagement is a key factor of this in this scenario. But I would like to enforce to the technology as a tool to get this objective. So not only we can get the efficient management of resources in agriculture, in water management, but also it's important for governance. New technologies like, I don't know, digital twin, blockchains, edge, cloud computing, etc. Every year we have new technologies, so they are tools to it's a mean of to get the maximum information for the governance to have a better decision for stakeholders, etc. And that's all for my side. Thank you.
Thank you so much, Miguel. Marco, please close this event.
Okay, it's 1 p.m. So in terms of time management, I think we did a good job. Well, you did. Everyone who presented, everyone who moderated, and everyone who made this happen today. I know that everyone has been thanking each other, but I cannot help but doing it as well, because I was very happy and proud to see after 3 years the projects, giving us information and sharing knowledge about what was done, and educating us on their, let's say, the results. Of course, I'm super happy to have had as well our water experts in the round table, because we received many inputs, and for sure that's very useful food for thought. I'm just trying to process everything which I heard today, I've listened to. Again, so much food for thought. I've heard some keywords like, for example, stakeholders and policies and policymakers, and trying to have some kind of real involvement of stakeholders and end users and people who can benefit ultimately from the results of the project. And also I've heard about comments about policies and trying to make sure that we are speaking a language that is understood by policymakers, and also trying to get the feed with the lessons learned and the evidence gathered by the projects and the knowledge gathered by the project, feed new policies in the water sector. So of course, these are things which are at the core of the PRIMA strategic research and innovation agenda, let's say the mission of PRIMA. And these projects are really what we are investing in as a tool to accomplish these objectives, okay? That are only part of our more overarching objectives, which we can summarize in making a positive impact at social, economic, and environmental level in the region, in the Mediterranean region, which is of course not easy, but I mean, we try to do this. Of course, I'm really happy that we received also some information about possibility to further cooperate, for example, within the for example, the World Water Council, with the Institute for in the Mediterranean Institute for Water, the possibility to extend the networks and make sure that the PRIMA projects that can collaborate further between them. Again, I second what Eddie said, that this hopefully just a starting point. And again, there's this interesting initiative, the Observatory on Non-Conventional Water, which is again something that we can explore further. There's the new exciting project on the Nexus community of practice that can be another chance to another tool, let's say, another facility for further cooperation and to further valorize the results that the projects are achieving. So, I mean, again, I'm very happy today with this webinar that I consider a success. I have to thank everyone who committed over the past months to preparing it, and today for the wonderful management. Again, also the PRIMA colleagues who are managing the Zoom application from the office and were in charge of the logistics, let's say. Great discussion. I think the outcomes we will be further exploring as outcome of this meeting. We will be further exploring how we can valorize the work of the projects. We can integrate them into other networks and spread the news also about PRIMA. So it's 5 minutes past 1. I would like to close now this meeting because everyone seems to be hungry or tired. It was very intense. Thanks again, everyone, for today's meeting, and thanks also to the people who've been following the event for 4 hours straight in a row. Thanks, everyone, and have a nice day, everyone.